Good morning. Good morning. Good morning. You can switch on your video if you want. You can switch on your video.
Good morning.
Hello, good morning to everybody. Good morning. Good morning. Good morning. Ciao. Nice to see you again.
Good morning.
So you can switch on your video if you want. You can switch on your video. Good morning. We are already on YouTube streaming. We haven't started yet the registration, so we will wait for everybody to be connected, and then we'll start. We are already 33. Good morning, Roberta. Good morning, everyone. Yeah.
Good morning.
Good morning.
Good morning to all.
Good morning.
Good morning.
Good morning. Ciao, Claudia. Good
Hello
morning.
to everyone.
Ciao. Good morning. Good morning, Roberto.
Good morning to everyone. Can you hear me?
Yes, very well. Good morning. Good morning. We are already on YouTube. If you want, I sent you the link, I think. Let me send you also in the chat, but probably no. So we started a streaming for those who wants to attend the seminar, also external to our group. Good morning to everyone. We will wait until probably 1 minute more, and then we'll start the registration. The registration has not started yet.
So today I'm connecting from Zurich.
Oh, good. So we see you very well. We hear you very well, Roberto. Okay, other people connecting now. So in the meantime, let me give you some instructions. I will start the registration in a couple of minutes. You can switch on your camera during the presentation if you want. Sometimes it's also useful for the speakers to see your faces while he speaks. Please, however, be sure to have your microphone off to avoid any noise like this one. And at the end, you will see, I will project the program for today very shortly in a minute, but during, at the end of the presentations and at the end of the day, there are different slots for questions and discussions. You are invited to participate to the discussion. You can make questions, you can share your ideas, comments. So the only thing is that there will be a facilitator, a chairman during the discussion, and please try to use the raise hand tool to book your turn. Okay, given that we are already 2 minutes late, I would like to start the registration. The streaming is already on. I start the registration now. Okay, so good morning to everyone. let me just short to give you my personal welcome. I'm very happy that this is the first MD multidisciplinary event that has been organized by all the faculty of the PhD in Sustainable Development and Climate Change. I will very shortly just project the program for today. You see, we'll start soon with Roberto Guizza, a short introduction, and then we have 4 different topics of a duration of 1 hour, including questions, answers, and discussion. You receive already the program for today by the PDF agenda I sent you before. Again, very, very welcome to this event, and let me give the floor to Roberto Guizza, who will introduce the event. Please, Roberto, go ahead.
Yes, thank you very much, Mario. I just want to say a few words of why we have designed this type of events for this PhD, and I will do that with the help of few slides that we have prepared, that the Consiglio di Coordinamento Nazionale have prepared with me. Okay, so Franco Flandoli, Elisa Giuliani, Claudia Lupi, Mario, Cristina Nali, Alberto Pirni, Alberto Poggio, and Denis Sarigiannis. So the idea of having this type of event, this multidisciplinary type of event, comes from our real life experience. So we are involved not just in research, but we are often also called to advise ministers or governments. I'm, for example, working right now with a minister for transport, where we're trying to design a new strategy for mobility, for the future, decarbonized mobility. So when you do this type of work, you have to be able to dialogue and understand the language of others, understand the way they see problems, and find together what are the best approaches to move forward. So this is why when we were designing this new PhD program, we thought that it was essential to have to expose everyone, not just you students, but also us researchers and academics, to working across disciplines. So this is the idea of this common horizontal MD event, multidisciplinary events. They are then supported also by curriculum-based events. There, the idea is that you will work more with people with your working in your area, but there will be interaction with people working at different universities. This is to help you connecting with other groups of people, with other scientists and academics working on similar topics at different institutions. Everyone has a different approach, uses different methods, has a different story. And so by exposing everyone to this type of curriculum-based event, you can actually see how the same problem could be approached in a different way. And finally, the idea of a PhD is that there will be most actually of the educational activities will be topical, will be will prepare you for doing the research in your specific area. The multidisciplinary event is going to be now at the beginning of a PhD. We will be this series of lectures, and then we will try to organize an event in presence. This will probably need to wait until May, June. And we haven't yet decided the date. It was supposed to be now, but we had to postpone it because of COVID. The idea there is that we will be actually working together. So see these lectures, the one you're going to follow in these 6 days, as a first exposure to problems as seen by people with different expertise. The idea of these lectures is that they should be at a high level, so that everyone, even people who do not have a background in the area of a lecturer, can follow them. And this is precisely to expose you to the fact that the same problem might need to be solved, interaction with experts of different disciplines, and could actually be solved only if other aspects are taken into consideration. Okay, I thought of giving you some personal experience of this, okay? Because if you want, until a few years ago, I mean, I was always working with people with different disciplines, but they were much closer to mine. I just want to tell you that actually real life now is becoming more and more multidisciplinary. Now, I used to deal with predictability of the Earth system, dealing with the complexity of a physical system. But when I moved to Italy in 2018 at the Scuola Superiore Sant'Anna, I started actually working more on climate. And as soon as you want to address issues linked to climate change and sustainability, you realize that the only way you can contribute to addressing the problem is to confront yourself with people coming from different disciplines. And I want to give you 6 examples of work that in which I've been involved in the past 3 years with colleagues. Some of the colleagues are actually here listening, others come from other universities. One is on climate and economic modeling. The second one is on climate change adaptation and agriculture. The third topic is on green transition, transformation, and ethics. The fourth is on climate science and epistemology. The fifth is on legal aspects of climate change. And the sixth is on climate impact on health. So I never done this type of work before I joined Scuola Superiore Sant'Anna. The last 3 years, I actually managed to do some work, and also we have written some papers. Some are still in the writing, some have been published in these areas. The first one is on trying to understand, for example, the role of taxation as a way to push forward a transition towards a decarbonized society. This work was done with Claudia Vines, who is now at Utrecht University, and colleagues from the Scuola Superiore Sant'Anna. And the idea there is that if we can build a model that can take global warming into account and include some feedbacks between the physical system and the economical system, then we can do simulations that take into account whether actions that we take, action that could have some economic impact, could actually trigger benefits for the climate system itself. The second one is on agriculture in Africa. Here we are looking at adaptation strategies, how to rethink the way long-term planning are done in countries who have already seen a strong impact of climate change. And what we are doing in this work, which is a EU project, the material that I'm showing is from Robele Tekele, who is sitting in Ethiopia and is working with us on this Horizon project, Focus Africa, is to try to understand how the physical system, the meteorological large-scale patterns affect the local weather and so can impact crop yields at the local level. The third area in which I've been working is with the colleagues with a philosophical background. In particular, I'm quoting here results of a work with Professor Pirni, who is one of our colleagues on the ethics of climate change. The realization of the importance of this temporal dimension, which is quite unique to the climate change problem, is essential if you want to try to understand why it is so difficult to take actions, to push politicians to take more impactful decisions. For example, when we meet at the COP meetings year on year, no, you see that scientists and the young people, a lot of people know about what's happening, is always unhappy about how slow are the motions and the decisions taken by the politicians, how vague they are. Well, you need to dig deep and try to understand this intergenerational aspect of the problem, to try to understand why there is so much difficulty in taking decision and how we could probably maybe change the language, or so that we can convince people that action is needed. The fourth is on epistemology. Again, this is work with a philosopher. I'm quoting from Bradley et al. And Roman Frakes, philosophers working at the London School of Economics. Why should they trust a model of the Earth system? A model might be realistic, as you can see from this image of the two Earths. No, one is a simulation, one is a satellite image. No, a model looks very realistic, but can I trust and use a model of the Earth system to take decisions that will affect the economy of my country for the next decades? What type of narrative can I use to convince people that they should trust the model and the science behind the model? The fifth area is on the use of legal tools and legal method to try to accelerate decarbonizations. No, you probably read that more and more groups are actually challenging a lot of companies and raising lawsuits against companies who have not done enough to address climate change, or government who has not done enough to address climate change. This is, again, another area where having a strong scientific support to the legal teams who are working on this area is essential to make sure that whatever the legal teams say is actually sound and based on observations. And the fifth is on identifying the co-benefits, for example, of a decarbonized future. Co-benefits that if we are able to identify very clearly by working together with medical doctors, we could actually, again, use this type of discourse and narrative to convince people to change. So these were just 6 simple examples on research, but not just research, and also real life work in which I'm involved. And I just thought of giving you some examples just to prove that the way we have designed this new course is actually based on what's happening. So I hope I've convinced you that it's good to be exposed to the language and to the methodologies and the tools and that the people in different disciplines use to address problems linked to climate change and health in this way. And I wish you all a fantastic MD workshop. Let's develop it further. Let's develop what I told you further and apply it to our research. Thank you very much. I stop here. Mario, back to you.
Thank you, Roberto. Thank you for this wonderful presentation, giving the panorama to the all disciplines involved in our program. So now let me give the floor to the first group of speakers. I think, Roberto, you will start, and then it will be Claudia, Lupi, and Dino Zardi. So please, Roberto, take again the floor.
Okay, I wonder whether, Claudia, do you want to say something about today before I start? Claudia, Lupi.
No, I think it's everything is very clear. I'm so happy to be here, and I want to say welcome to all our students. I'm Claudia Lupi. I'm the coordinator of the Curriculum 1, the reference person for this curriculum. So Roberto, please, you can start.
Okay, very good. Thank you very much. I now put on my hat as a professor in physics and expert of the Earth system. And I want to give you some brief introduction. So let me just share my presentation. Okay, and I'm going to give you the first lecture of today. Curriculum 1 will drive you through some interesting areas of research linked to the Earth system. So the talk is about the key components that determine the Earth climate. I will try in 15 minutes to give you a brief summary of what we need to take into account if we want to understand how the climate has been changing and predict how the climate will be changing. Okay, so in my lecture notes, you will see a brief summary of what I'm going to talk. I'm not going to read it now. You'll find it in the PDF that we will share at the end of the day. The first point that I want to make is to make it clear that there is a difference when we talk about weather and when we talk about climate. Clearly, the two are linked. When we talk about weather, we usually talk about atmospheric or oceanographic, or say phenomena that we experience. We experience weather, we do not experience climate. Weather events are what we experience every day. Weather events are what causes damages, if we think about extremes. With the term climate, we mean average, the average of weather events, the mean temperature over a long time period, the mean, or say the statistics of weather events computed over a long period. So when we talk about climate change, we mean that the climate, so the average, say the average conditions, the statistics of the weather computed over a long period, let me say 20, 30 years, are changing. So if I compare the average conditions of the summers between 1990 and 2020 to the summers of 1950 to 1980, then here I'm comparing the climate of two periods, and I'm talking about climate change and climate trends. Now, when you see graphs that illustrates how the temperature is warming, for example, here we talk about annual averages. Annual averages are affected by some natural variability. So to have a good idea, a good and a solid, robust understanding of whether the climate is changing, one cannot simply look at the annual averages, but you should look at longer period. So the first point I want to make today is this. It should be clear in mind to all of you that weather is what we experience, and the climate, with the term climate, we mean average conditions. So when we say that the climate is changing, we mean that the average conditions are changing. And why are they changing? Well, because something in the Earth system has been changing in the past 150 years. And I want just to remind you a few points about the structure of the key components that determine the climate of the Earth. The first one is the atmosphere. What you see here is a vertical profile of the atmosphere from the lower part, the troposphere, from the surface, we have temperature that decreases up to a level called the troposphere. This is usually around 18, 20 kilometers. The fact that the temperature has this type of slope or changes is essential to understand why, for example, water vapor is confined in the lower part of the atmosphere, or why weather phenomena happen mainly in the lower part of the atmosphere, so the troposphere. After the troposphere, there is about 30 kilometers of mass of air, during which the temperature decreases as we go up in the levels till we reach the so-called stratopause, and then this is followed again by a decrease in temperature, and then by a further increase. So the stratopause, the warming in the stratopause, is linked, for example, to the absorption of radiation by ozone, O3. Ozone is a key component of the atmosphere that absorbs ultraviolet radiation from the sun. The presence of ozone and the fact that it has been absorbing a large part of the ultraviolet radiation coming from the sun has made it possible for life to develop on Earth, for example. Clearly, the exact vertical profile depends on where you are on the Earth. It changes between the equator and the high latitude. The point I want to make with this graph is that you cannot expect weather or climate to be the same everywhere in the atmosphere. The equator, for example, is characterized on average by higher temperature because it receives more energy than the higher latitudes. The tropopause is at the higher altitude because as we have warmer surface conditions, the air is warmer, can rise up to higher level before being cooled down. As you move towards the equator, towards the poles, you see that temperature decreases, and also the position of a troposphere changes. The climate, and here, let me say the seasonal average of the temperature of the Earth is clearly determined by where you are and by the seasons. Here you see two maps of for example, of the average temperatures in January and in July of the Earth. You see, what I want to point out with this graph is that the average conditions are affected by the land distribution. You see that the continents tend to be colder in winter, warmer in summer. Second point is that there is an asymmetry between the two hemispheres. Okay, so you see that the North Pole becomes colder in the boreal winter than the South Pole in the Southern Hemisphere winter. Okay, so this is why, if you compare what's happening in the Northern Hemisphere, think about the melting of the sea ice, of the Arctic sea ice, and you compare it with the melting of the sea ice in the Antarctica, they're not exactly the same. They're not happening at the same rate because the two hemispheres are not similar in terms of distribution of the land, in terms of the ocean circulation. Okay, let me skip a couple of slides. The other second point, so the atmosphere, the way the temperature changes in the atmosphere is determined by its composition and determines the climate condition at the surface. The composition of the atmosphere is another key aspect that one needs to take into account to understand the Earth climate. note that most of the atmosphere, 75%, is composed by nitrogen and 23% by oxygen. The so-called greenhouse gases are actually a very small percentage of the atmospheric composition. Water vapor on average 0.3%, carbon dioxide on average 0.05%, methane even less. So first point on this table, water vapor is the greenhouse gas which has the largest composition, but because of its cycle, because of the way water vapor, of the cycle of water, we are not too worried about it. What we are worried about is actually the other two greenhouse gases, carbon dioxide and methane. Tiny percentage of the atmospheric composition that can actually play a very important role, as you will hear from colleagues afterwards, when they talk about the energy balance of the atmosphere. What you see in this graph is the distribution of humidity as we move a different latitude at the equator. The two red curves, you see that the concentration of water vapor is higher. As we move towards the pole, it is lower. Water vapor is a way to actually, so water vapor is used by the atmosphere also to exchange heat and energy among different masses of air. If you warm a mass of air at the equator and you make it, and because it includes a lot of water vapor, when you transport it towards the northern latitudes and you cool it down, by cooling it down, you can release heat, the heat linked to the condensation of water vapor included in the mass of air. The ocean is the other important component of the Earth's atmosphere. The ocean contains 97% of the water on the Earth. The ocean plays a major role in distributing heat which is mainly absorbed at the equator, and it's then exported towards the high latitude by the western boundary currents. For example, the Gulf current is one. The ocean also transports cold water, cold and heavy water and salty water, which is generated at high latitude in the Atlantic Ocean, one close to Greenland and one in Antarctica. So it's transported towards the equator. So by way of a deep ocean circulation, by ways of using deep currents, the ocean distributes heat and makes it, and plays a major role in determining the climate of the Earth. Think, for example, of the role that the Gulf current has in determining the climate of Europe. Other three key components that determines the Earth climate are the cryosphere. The cryosphere, so the way ice is distributed over land, plays a key role because ice is a very reflective surface. If you have a surface covered by ice, it reflects a lot of incoming solar radiations. If you melt ice and you replace it in the Arctic, for example, by open water, then you replace a surface which reflects a lot of energy, incoming solar radiation back to space, by a media, the water, that absorbs a lot of part of this radiation. So by changing the albedo of the atmosphere, you can have an impact on the Earth climate. So the cryosphere, the distribution of sea ice, the way sea ice is distributed, plays a big role in determining the Earth climate. Snow cover in winter, for example, is one aspect that determines changes in the Earth albedo and also determines the climate of the different parts of the world. So a melting of the ice, a reduction in the snowfall in winter could lead to changes in albedo, which could trigger further changes to the Earth climate. I talked about the role of a land surface, the distribution of land. The way land is distributed affects how the surface warms, but also affects the ocean currents and the way the heat is distributed among the different parts of the world. And the fact that the hemispheres do not have a symmetric distribution of land is the key reason why the climate change, the warming that you detect in the northern hemisphere, in part of the northern hemisphere, I'm thinking also, for example, about the Mediterranean, you cannot detect it in the southern hemisphere, where most of the hemisphere is covered by water. And finally, the biosphere. The biosphere, so how vegetation, for example, growth, is very important in determining the climate condition close to the surface. It regulates the temperature, it regulates the distribution of heat, and it regulates also the distribution of water vapor in the atmosphere. So deforestation, for example, plays a huge role in determining climate change, because if you replace a surface which has one type of vegetation with another, you can again affect albedo, you can affect the way water vapor is extracted from the soil and is evaporated, and this can affect the global climate if you do this on a large area like on the Amazon, in the Amazon forest, okay? And with this, I conclude this very brief overview of the key components that determine the Earth climate: ocean, atmosphere, sea ice, biosphere, the distribution of land. All this, the way, all of these aspects determines the climate. So you can understand why, for example, there are talks about climate hotspots, areas of the globe that warms more than others. This is linked to the geographical configuration, to whether, for example, there are close by ocean currents that bring heat or take away heat, and so on. And with this, I stop here and I pass the floor back to Claudia. Thank you very much.
Thank you, Roberto. Maybe we can ask some interesting question to Roberto at the end of the slot. So we go very quickly to next presentation. Yeah. Where is here? Okay. You can see my screen?
Yes.
Yes, thank you. So move on the next topic, that is about paleoclimate. And in particular, we know now from Roberto's talk that climate is the end product of interaction between several components, and all these components are connected, and the main driver is the sun. the heat stored by the greenhouse effect is then transported by atmosphere and the ocean from low to high latitudes. The planet in this way is favorable to the life since a billion of years. And in this picture, we can see a very simple model of the climate system. There are the two components: atmosphere, ice, ocean, land surface, vegetation, and they are closely related to each other. And we have three main external causes able to change the amount of heat that the planet receives. They are changes in plate tectonics, in Earth orbit, changes in sun's strength. When an external forcing acts on the climate system, each component responds and tries to restore balance to the system. The reaction of the climate system are the climate variation. For example, changes in the atmosphere composition or changes in the volume of ice at the high latitude. Three external causes act on the climate system by varying the amount of energy received, and they operate at different time scales. The plate tectonics processes act on a time scale of millions of years. Earth's orbital parameters operate on time scale of hundreds and tens of thousands of years. And finally, the solar forcing acts on time scale shorter of decades and century up to thousands of years. In this figure, we can see just the 65 million years of the Earth history. In the geological time, paleogeography has varied many times, and land and ocean have received and distributed different amounts of energy, of solar energy. The planet has experienced different climate conditions. It went from an almost completely frozen land, similar to a snowball, to other time when it was extremely hot. Geologists and paleoclimatologists distinguish warm phases, like over there, without ice at the high latitudes, as greenhouse or hothouse, warmhouse world, or cold phases with very big polar ice sheets, indicating them as ice world. So today we have ice sheets in Arctic and in the Antarctica region. So we are in ice house world condition. We are over there in this thin time interval. At the scale of tens and hundreds of thousands of years, the orbital cycles of the Earth regulate the amount of solar radiation received. We know three orbital cycles called Milankovitch cycles. They are eccentricity of the orbit, inclination of the Earth's axis, and precession of the equinoxes. These cycles change the distance of the air from the Earth from the sun over time, and change the energy received at the different latitude. The last external cause is the solar forcing. Because it's very short today, I won't talk about it. The climate variation of the past could be studied through archives and proxies. Archives are natural features of the Earth, like ice core or sediment from the ocean, sediment from the lake, tree rings. And proxy are geochemical, physical, geological, and biological measurements obtained from the archives. Proxies are surrogates data for measurements from ground-based instruments and satellites. Proxies provide information about temperature, ocean circulation, sea level, ice volume, and the interaction of Earth and other planets affect the amount of incoming solar radiation, the insolation. At first, in 1941, Milankovitch integrate the effect of all astronomical parameters and compute the insolation at the top of the atmosphere. The insolation minima were associated with major alpine glacial advances, so proxy, recorded by geological evidences. But to verify the Milankovitch theory, it's necessary to have the mathematical tool, that is the Fourier analysis, and a good set of data. We need data from a continuous, high-resolution paleoclimate record. And among paleoclimate archives, ice cores are one of the most important archives because they are continuous and with high resolution. They are accurately dated, and a lot of different measurements could be performed on the same archives. Ice cores are collected from Arctica and Antarctica. One of the most important projects is EPICA project in Antarctica. And the ice core contain air bubbles. Air bubbles trapped in the ice core provide a record of the past atmospheric composition. We can analyze fossil atmosphere over the past 800,000 years. It's amazing, I think. And we can take a look at this data. With this graph, we try to understand what it means that climatic variation present oscillation on the orbital scales. Here, in the CO2 record from Antarctica, there is an alternation between cold, so glacial, with very low content of CO2, and warm interglacial with high content in CO2. The oscillation show a typical sawtooth trend. In each cycles, it can be distinguished 2 minima in CO2, for example, here, 2 minima in CO2, interspersed with a maximum in CO2. If we perform a time series analysis, we can find that the glacial phases have occurred every 41 kiloyears between 8 to about 500,000 years. Then the glacial cycles lasted about 100 kiloyears from 500,000 years to the modern time. Moreover, in each interval, the warming phases, this one, for example, called deglaciation, is rapid, while the glaciation, the other one, phase, is low and long in time. This trend is also respected by other environmental parameters, such as air temperature. For example, here, the comparison between CO2 content and a proxy for temperature in the ice core from EPICA. Between glacial and interglacial phases, we record a change of about 9 degrees Celsius from cold glacial phase and warm interglacial phase. Moreover, some interglacial of the past present the same insolation of the modern one. For example, marine isotope stage 11 marine isotope stage 5 are very similar in CO2 content and temperature of the modern interglacial called marine isotope stage 1. So we can study these analogs to understand the natural evolution of a warming interval, and we can document its duration. All this information is fundamental to understand if the current interglacial is comparable with the climate history of the Earth or not. We want now to compare the paleoclimate system, the climate without our complex societies, with the modern climate system. So at the end, here the curve about carbon dioxide, at the end of the last glaciation, the CO2 concentration was about 190 ppm. After 10,000 years, CO2 reached 265 ppm. And at the beginning of the Industrial Revolution, the ice cores document 280 ppm. Let's try to do some calculation to compare the last glaciation to modern warming. In the last 10,000 years, CO2 has increased by 73 ppm. The accumulation rate was 0.007 ppm per year. Remember this number because it's very important for later. And here we go to more recent time. This graph plots CO2 data from the past 60 years. The data come from the Mauna Loa Observatory and they are available free of charge. So you can take a look, here are the links. Let's pay attention to a couple of CO2 value and try to calculate the CO2 accumulation rate. In the 70s, the CO2 concentration was about 325. In the 2010, about 390, and in the 2020, 412. So at the beginning of the Industrial Revolution, the CO2 was 208, in the 70s, 325. So 45 ppm in 220 years. With an accumulation rate of about 0.22 ppm per year that compare to the beginning of the deglaciation, this accumulation is increased 30 times. Then from the 70s to 2010, the accumulation rate increased from 0.22 to 1.6 ppm per year. So the accumulation rate increased 7 times. And in the last decade, the accumulation rate has increased again and reached 2.3 ppm here. So in conclusion, it seems that over time, the climate system has become more complicated and probably a new element, a new forcing must be added. This new forcing must be able to vary the quantity and the speed with which greenhouse gases accumulate in the atmosphere today. Where does this CO2 come from? I think Dino Zardi will help us understand more about this mystery. And thank you for your attention. I hope to be in time. If you have some comments, or we can go to Dino, what do you prefer?
Probably we can keep questions at the end of the slot.
Yeah.
Claudia, so we move to Dino. Thank you very much.
Good. Thank you.
Please, Dino, you can take the floor.
Thank you, Mario. May I share my screen?
Yes, you can. Please go ahead.
Can you see it?
Yes, very well. Thank you, Dino.
Great. So thank you very much, Mario, and thanks, Roberto and Claudia, for your nice introduction. I will more or less start from where Claudia left us. So she gave me a very nice introduction. So I will skip all the details about the processes that she has described quite clearly and show another version of this long record of temperature and of carbon dioxide, as we'll see, in the history of our planet. What we notice is that today we had a very sudden jump, sudden compared to the typical scales of climate systems. So it's a jump occurred in some decades, but it's very fast compared to the long processes occurring in our Earth. What did this imply to the temperature? We can have a look at it closer to our days from a picture which is provided by the National Oceanic and Atmospheric Administration of the United States, which is quite popular and you might be already familiar with it. You see here two graphs. One is a solid line, and the solid line represents CO2 concentrations evaluated at global level. And you can have an idea of the values on the right-hand axis, where you see global carbon dioxide concentrations in ppm. The bars, the blue and red bars, refer to temperature anomalies. And in particular, we have temperature anomalies at a global scale. So we have the global average of surface temperature in the atmosphere compared to a reference value. Now, you can clearly see how the two variables are strongly connected. In particular, we had clearly most negative anomalies of temperature before 1940, then a period in which we have a mix of the two, and then after the 80s, we have increasing and always positive temperature anomalies. So this somehow suggests a connection between the two. Concerning the increasing amount of CO2 in our atmosphere, it is quite explicative to have a look at the recent updates. Notice that this is the update of January 2022, so very last day data. Concerning the global average value of CO2 concentration. As you may know, there is a network, a well-established network of monitoring stations for CO2 concentration all over the globe. The most famous of the station is probably that based at the volcano Mauna Loa in the Hawaii, which was established by Keeling at the beginning of the 1950s and has been working since then and is still a reference station for this kind of measurements. What you see here is the mean, monthly mean value in red. And you can notice a cycle, an annual cycle, which is clearly linked to the seasonal effects connected to vegetation, which typically drains CO2 from the atmosphere when the vegetation is most active and less when it is inactive. Whereas the black line is the smoothed, which means the filtered average with a moving window average, which gives you an idea of the trend, which is quite constant and it is increasing. And notice that, well, before 2017, we have passed the 400 ppm value, which seemed in the past quite impossible to reach. The reason for this abundance has to deal with a very complex series of factors composing the biogeochemical cycle of carbon. Here you can see a picture of the various interactions and exchanges of carbon through the different planetary components. including the earth crust and soil, vegetation, the atmosphere, the ocean. And you should distinguish in the ocean the surface of them, where many biological effects occur and where you have the most active interaction with the above atmosphere. And then the deep ocean, well, of course, life is less present, and where you have the deposition of many sediments, which have been partly produced by biogeochemical cycles, like the formation of shells, the effect of foraminifera, and other factors. So the exchange of carbon is such that vegetation tend to sequestrate CO2 from the atmosphere and convert it into water vapor and oxygen. And this factor has been working for millions of years and has strongly modified the original atmosphere of our Earth, which was very rich in CO2 after volcanic emissions. And nowadays we have an atmosphere which is very rich in oxygen. Of course, all of these processes have different factors governing them, and, which is most important, different time scales. Notice here the effect of human emissions, which appeared strongly in the last 2 centuries after the industrial development. And let's pass to the other picture, which shows something similar, but with an emphasis on time scales. Notice that all of these arrows represents the same processes we have seen in the picture before, but with different colors indicating different time scales. In particular, notice that the red arrows mean very fast processes compared to the scales of our Earth, which is 1 year. Then you have yellow arrows, which means fast, 1 to 10 years. Then light green, which is slow processes, 10 to 100, and then dark green, very slow. You notice that the slowest processes occur in the ocean. So the exchange of carbon from the surface to the sediments is very small. This is a typical set of sequestration. CO2 can be dissolved into the water of the oceans, and in the waters of the ocean, it can be transformed either by photosynthesis or by the sequestration from some animals and various kinds of living bodies who can use the carbon for producing shells, skeletons, and so on, and then get sedimented. So the ocean is a big absorber of CO2, but a very slow one. On the opposite, you see that the fossil fuels that get emitted from combustion, and especially for industrial activities, transportation, house heating, and whatever, emit a huge amount of CO2 in very small times. And the imbalance between this slow sequestration and fast emission is the main reason for this strongly increasing amount of CO2 in our atmosphere, which we have been outlined at the beginning. What has this to deal with the temperature of the atmosphere? What is the connection? To understand that, we should look at the annual energy budget of our atmosphere, of our planet, actually. Now, consider the incoming radiation from the sun, which is more or less a constant to our planet as far as our sun is constant in its activity. And so we can estimate it by means of a number, which is very important. It's named the solar constant, 1,368 watts per meter, which is the energy which passes every square meter per second of a surface close to the top of our atmosphere, so close to the surface of the planet. Now, this is reaching our planet on a disk with a radius equal to the radius of our planet, and it gets distributed due to the Earth rotation over the whole surface of the globe, which can be approximated as a surface of a sphere of the same radius. So if you distribute all of this incoming energy or incoming power to the surface, you get an amount of 342. But to be more precise, we should not forget that not all the incident solar energy, S, the solar constant, gets involved into the budget. Part of it is reflected. And the coefficient A, which tells us how much it gets reflected, is named the albedo. So on average, the Earth albedo, which is due to a series of factors, including clouds, including water surface, leaves, and any reflecting surface in the planet, amounts to about 30%. So if you refine your budget and you exclude the reflected energy, which doesn't enter, of course, the budget, it gets just backscattered to your evaluation, you get a more precise estimate of this gross amount of energy, which amounts to 239 watts per meter. Now, if you remember that you can somehow approximate the emission by our planet as a black body emission, so the irradiance E equals the constant of Stefan Boltzmann sigma by the fourth power of the radiative equilibrium temperature, Ta, you get an estimate of the radiative equilibrium temperature of our planet, which amounts to 2055, which is minus 18 degrees Celsius. This might seem strange because it's very unlikely that we feel such a temperature, but you should not remember that in our very rough model, we incorporated into this sphere all their components, so including the Earth's surface, the atmosphere, and whatever. So in order to get a more realistic model, we might probably need to revert to something more detailed. Now, remember that having an emitter of 2055 kelvins implies an emission over this kind of spectrum of the wavelengths of the electromagnetic spectrum, so mostly infrared radiation. Whereas the sun emits at much higher temperature, almost 6,000 kelvins, and that's the reason why the emission of the sun is around the so-called visible electromagnetic spectrum, so the short wavelengths. If we want to refine more the model we used, we should include at least 2 layers. So not only the solid surface, but also the gaseous components. So this is a more refined budget. So we have the incoming radiation E, which gets partly absorbed in the visible part of the spectrum by an absorption coefficient AV. So what you get at the surface is not more the whole E, which you get at the top, but a reduced value, 1 minus the coefficient in the visible E. Based on that, you must have an equilibrium with the emission by the surface, which is not known at the moment. But you should also remember that while passing through the gaseous component of the atmosphere, this emission gets absorbed in turn. And so what comes out of the top of the atmosphere is what remains after AIR, which is the coefficient of absorption in infrared, a subtracted part of the irradiance that gets emitted. Also, the atmospheric body, which is in between, emits in turn on both sides, so towards the space and towards the surface. So in this 2-component model, where we have one component is the surface of the planet, and the second component is the atmosphere, we need to get a balance between fluxes at the 2 surfaces bounding them. So at the upper surface, we have that the incoming radiation needs to balance the outgoing radiation emitted either as a result of what remains from the emission from the surface and the emission from the atmosphere. And at the surface, we have that the incoming radiation from the sun, apart from what was absorbed by the atmosphere in the visible spectrum, it balances what emits the surface and what gets from the emission of the atmosphere. So if you write down the 2 balances, you get a very simple linear system with constant coefficients, from which you can get the 2 irradiances, the surface and the atmosphere, and in turn, using again Stefan Boltzmann law, the equilibrium temperature. Notice that for the case of the surface, we can assume that it is a perfect black body, so obeying exactly the Stefan Boltzmann law. Whereas for the case of the atmosphere, we should remember that it is not really a black body, it's a gray body. And so we need a corrective coefficient, which is an emissivity epsilon. And due to Kirchhoff's law, we know that epsilon is equal to the absorptivity in the same spectrum. So we can use the absorptivity, AIR, as a coefficient equal to epsilon. So if we go to the calculation, we solve the equation, we get a values for the emission by the surface, the emission by the atmosphere, and the two temperatures. Now, if we want to get definite results, let us assume that the absorption in the visible is quite small, as it is typical of our atmosphere, which is quite transparent to the shortwave radiation, whereas it's quite absorbing in the infrared. If we substitute there, we get that the emission from the surface is 1.5 what is getting from above, so much larger than we've seen before, whereas the emission from the atmosphere is much smaller. As a consequence, you get more realistic values of the two different bodies, the surface and the atmosphere. And as you can see, although this is a very simplified model, we get something explaining us the difference in temperature of the surface from the atmosphere. Here we see a graph where we can estimate how the two temperatures, Tx, solid red line, Ty, solid blue line changes, read on this axis, and the two irradiances, X of the surface and Y of the atmosphere change depending on the changes on the infrared absorption. So since the infrared absorption in the infrared part of the spectrum depends on the concentration of greenhouse gases, so for example on CO2, you can understand that with an increasing CO2 concentration, we had an increase in AR from 0.8 that we have assumed at the beginning, theoretically up to 100%, which we hope we don't reach in our atmosphere. But by increasing the absorption coefficient, all of the budget increases, and in particular, the two temperatures are expected to increase by significant values. This is an explanatory model that allows us to understand what was evaluated with much more sophisticated models by the Intergovernmental Panel on Climate Change in order to answer a question that was raised by the agreement, the Paris Agreements. What should we do to limit the increase in temperature at global scale to at most 1.5 degrees Celsius? You can find the detailed description of all the procedure that was set up at this link. I just show you some details. I don't want to be fully complete in this description, but you can capture the essentials. The exercise that was made is, let us assume that we can reach at the global scale a zero net emission situation of CO2 by two given dates. The most optimistic one in 2040, the less optimistic in 2055. So we have a schematization on how the planet would do if net emissions of CO2 at global scale would get reducing at a faster scale to 2040, blue line, or at a slower scale, but at the latest by 2055. This is the emission. Of course, if we stabilize emission to zero, we stabilize concentration to a plateau level, which will be some smaller if we get that stabilization earlier, a little bit higher if we get that stabilization upper. Now, we concentrated on CO2 for simplicity, but we should remember that, as Professor Witz explained, CO2 is not the only greenhouse gas. So there are other important gases that cannot be easily controlled. But in any case, let us assume that we can get a stabilization also of these gases by some date, and this will be the purple line if we cannot reduce them, but they can continue increasing, whereas this is the situation in which we can decrease them. What happens apart from emissions to the temperature? This is a final result of the 1.5 degree report, showing us the expected values of global mean temperature as a consequence of these three different scenarios. You see here that we have a very scattered line representing monthly mean global temperature recorded from 1960 to 2017, right before the paper was published. As you can see, apart from the natural variability, you see the orange line which represents the trend. And what you would be naturally led to estimate is if you extrapolate that trend to the level of 1.5, you would get that value by 2040, and you would be expecting that this increasing trend would not stop unless you react as we have said before. So in the most optimistic situation, which is the blue line, the estimate provided by the different models that were run to get this forecast lies within this confidence band. So you see that at some stage, the temperature will be decreasing at a relatively fast rate in the range explained by this confidence bands. In the less optimistic situation, which is the gray line, you will get to some maximum and then get back to lower values by a later date. And in the even less optimistic situation in which you don't have a real reduction in other greenhouse gases, you will get to this very high values, which are possible, actually, very unlikely to reach, but not impossible, which is a very difficult situation. In any case, notice that what we expect, even in the most virtuous behavior, is that we are shifting to a climate which is definitely much warmer than we were expected before, which requires that for the next decades, we must get ready to face the consequence of such warming, of course, while acting in order to reduce them at the scales that the planet will allow us. So I hope I've been keeping on my time. I hope not have exceeded too much, but I'm available, of course, to take questions.
Thank you, Dino. So we have 5 minutes, I think, for questions or comments. If you want to, you can write on the chat or raise your hand. We are waiting for you, dear students. No comment. Oh, yeah, Federica, please. Federica Verrazzotti.
Exactly. Hi, everyone. I have not a question, but is a comment, if it's permitted. Yeah, that I really appreciate your energy. And for the other student, I am curriculum 1. As you know, Claudia Lupi, Professor Buizza, Zardi, etc., they know that my PhD project regards the future geological trends up to 2100 of sea level rise. And so in this presentation, I found some mix from climate aspect to the atmosphere to the past and future trends. Thank you. Thank you for your energy and thank you.
Thank you, Federica. Thank you, Federica.
Sorry if it's not a question, but I really found really interesting. So thank you.
Thank you so much. So move on to Tosin Afeniforo, I think is the next one.
Okay. Can you hear me, please?
Hi.
Okay. Yeah, thank you very much for the presentation. And especially in the aspect where Professor Claudia was trying to do some comparison between the paleo and modern climates, that began since the industrial revolution in the 18th century. The CO2 increasing from the 280 parts per million to what we have currently. And that's very interesting, and it's also causing some warming. And moving on to what Professor Dino was talking about, the deep sea absorbing the CO2. And I just asked this simple question to ask. Like we all know that I want to ask, does warm water actually absorb less CO2? Does warm ocean actually absorb less CO2? And if it does absorb less CO2, what is the fate of other CO2 in the atmosphere? What is the fate of other CO2 in the atmosphere? Does that mean we're going to have more warming at the end, of the day, if the oceans becoming warmer and warmer due to increase in temperature? Okay. Also, I have this second question to answer. We'll be talking about CO2 and CO2 and CO2. I think we have other gases also, which is also contributing to greenhouse effects. What about methane? And I know that methane has 36 times more potent than CO2 in causing greenhouse effect and also affecting climate change.
Okay, thank you. Very interesting questions. Roberto Ordino, some comments from you?
How much time do we have?
Yeah, because it's a very big deal. Yeah.
Dino, why don't you start? Yeah, Dino, why don't you start?
Yes, Tosin, I appreciate your questions because they open very interesting aspects that deserve a deeper explanation. Today, we only gave a first introduction just to make you curious and attracted to the topic. What you say is true. There are many different greenhouse gases, and some of them are even individually more powerful as greenhouse gases. For example, some synthesis compounds, for example, sulfur hexafluoride, SF6, which is used in industrial processes, is 13,000 times more powerful than CO2. So even small amounts may have a big effect. And in order to prevent emissions, you need some bans, as was made with the Montreal Protocol for CFCs and other compounds in order for the protection of ozone, apart from the fact that CFCs are also greenhouse gases. So there are different policies concerning whether they are mostly industrial emissions or emission connected to other topics. For example, methane is mostly produced by animal and then zootechnical activities, but also from natural sources. You may know that marshes and other wetlands are actually producing methane. So it's a very difficult question how to manage different sources of different greenhouse gases, and that required specific prescriptions. Concerning the oceans, I'm not expert of ocean, but what you should keep in mind is that actually the oceans are big storages, both of energy, because they absorb actually heat. And so the increase in temperature of the ocean is a great absorption of energy. Also, they are great absorbers of carbon, but the capability of the oceans of getting carbon dissolved is inversely proportional to the temperature. So the higher the temperature, the less the amount of carbon that can be stored. So one of the problems, one of the positive feedback of climate change is that an increasing temperature of the ocean reduces the storage capability of the ocean with respect to CO2. And the other important effect is the fact that in the ocean, two processes take place. The photosynthesis from algae or other plants. And in this respect, the oceans are great converters of CO2 into oxygen and water. And the other one is the sequestration determined by foraminifera and other living bodies who transform dissolved carbon in some form or mineral, quasi-mineral carbon that gets permanently combined and is very difficult to be released again. So this is the basic dynamics of carbon in the ocean.
Yeah, let me add on your question, why do we always talk about C or CO2 and not methane or other gases? So CO2 is probably is about 75–80% of the greenhouse gases that we emit. When we talk about, when we talk about the CO2 is increasing, actually we should say greenhouse gases are increasing. Other point, methane has a shorter life in the atmosphere than CO2. So if we stop tomorrow to emit methane, in about, I think, 20 years or so, the concentration will decrease, say, by 50%. For carbon, again, Dino tried to explain there are different sinks, different ways in which carbon can be removed from the atmosphere. If you average all the processes and so on, you get that the life time of carbon of C in the atmosphere is few hundred years. Okay, so this is why also CO2 is more concerning than methane. But it's also true to say that in the past decade, as the polar region have been warming, as permafrost has been melting, higher amounts of methane has been released in the atmosphere. So this is why now there is more talking about methane as well. Furthermore, as we've been trying to reduce the use of coal, a lot of countries have been using more gas, and gas means methane, which means again that the emissions of methane have been going up. So somewhere you're right to say we should also talk about methane. And indeed, in our language, we should have talked about both gases. But whatever we have said about CO2 is probably valid for methane. The times are a bit different. The relevancy is different. The sources are different, but the main concepts are the same.
Yes, thank you, Roberto. Maybe we can collect all these questions and discuss later in the next week in specific MD talks. What do you think? Because there are many questions now, but we are a little bit late. Could be a way.
May I suggest to write all the questions in the chat? The chat bot is recorded as the meeting. So when we will distribute the recordings, we will distribute also the chat. So you can not only write the chat, but also the speakers, if they have time, they can probably write short answers, or they can just put links on that. That is an important piece of information even for the following meetings. You know, all the topics that we think deserve to be looked in depth. We can you know, make specific webinars in the future. So I leave now again the floor to Claudia.
Yes, so we can go to the next slot about air quality and climate change. I think Michela Maione could be the first one, the chair of the session. Yeah, thank you.
Can you hear me?
Yeah, perfectly, please.
Okay, so good morning to everybody. Today I'm going to talk about equality and climate change and how these two issues that are now have been for a long time considered as separate, both by science and policy, are actually strictly linked, both for water emissions, atmospheric processes and chemistry, and mitigation options are concerned. And in this sense, I will also talk about methane, so reply probably to the question that have been posed before. So we have already seen how the warming of the climate system is affecting the globe, but also air quality has a stronger impact in in fact, degraded air quality is responsible for millions of premature deaths all over the globe every year due to the exposure of the population to harmful pollutants such as ozone or NO2 or particulate matter. But both climate change and degraded air quality are driven by changes in atmospheric composition that in turn are due to anthropogenic emissions, essentially due to anthropogenic emissions, and especially to combustion processes. At this point, also for considering the presentation that will follow, I think that it is important to introduce the concept of emission and the difference that is that exists between emissions and concentration. There are two terms that are frequently confused. So an emission is the amount of a species that is released into the atmosphere from a specific source in a specific time interval. And these emissions are causing the changes in concentrations that is actually the amount of a species in a volume of atmosphere. So in other words, it's like to say that emission is the flow of water into a water tub, while concentration is the water that remain in the water tub. So on the left-hand side, you see how emissions of the main greenhouse gas, CO2, have changed over the last 60 years. On the global scale, with the variation that are due to the various global crises like the COVID-19 pandemic in the last few years. And these anyway increasing emission have caused the increase in CO2 concentration, as showed by the famous Mauna Loa CO2 record. So we are dealing with changing in concentration of compounds and due to the change in their emission. So when we talk about climate change, we have to deal with the compounds that are really stable, like CO2 and the other well-mixed greenhouse gases that have long lifetimes, so they cause a global problem that must be tackled with global policies that will give longer-term results. But when we talk about degraded air quality, we have to deal with compounds that are much more reactive, so they have short lifetimes and represent a local or regional problem that must be tackled through local or national policies that are likely to give results on a much shorter time frame. So the impacts, of course, are global when we talk about climate change, but when we talk about air quality, degraded air quality, we have these impacts on human and ecosystem health that are on the local scale. Then the set of measures are more or less the same, but in the case of climate change, we have more structural changes are prevailing, while in case of air quality, we use more frequently control end-of-pipe technologies. And which are these compounds? Was concentration, changing concentration are worrying us. So for water climate is concerned, we have the stable greenhouse gas that are presented in the left part of my slide. These are the long-lived, well-mixed. These in particular are the greenhouse gases that are regulated under the Kyoto Protocol with their emission sources. is important to notice that the Kyoto basket does not include other important climate forces, warming agents like tropospheric ozone that must not be confused with the stratospheric ozone that protect us from UV radiation, and black carbon, that is the warming component of particulate matter. So these two species are also pollutants because are harmful to human health and are much shorter lived with respect to the well-mixed greenhouse gases. So they are normally dealt with air pollution policies. So if we look at the pollutants, those that are, for example, in air quality directives, we see beside the already mentioned tropospheric ozone and black carbons, other components, including the reflective particulate matter that has a cooling effect on the climate. So an effect that is opposite to that of greenhouse gases. And looking at this set of compounds listed on the right side part of the slide, you see that in many cases, the source sector is the same as greenhouse gases. It should be noticed that tropospheric ozone does not have any direct source, but its formation is due to photochemical reactions that are occurring in the atmosphere in presence of precursors like nitrogen oxides and volatile organic compounds. So how these agents are affecting the climate? This is a plot from the latest IPCC report where you see how the anthropogenic climate forces have changed the radiative forcing of the planet from 1750 to nowadays as a consequence of the changes in their atmospheric abundance. So on the right side of the axis, you can see the well-mixed green, the warming agents, and on the left side, the cooling agents. Among the warming agents, of course, we have the most important are the well-mixed greenhouse gases, but you see also the ozone in light green and black carbon. And if you look at the left-hand side, the cooling agents, you see that the main actor is actually the particulate matter, and the sulfate is a precursor of particulate matter that is cooling the atmosphere. And the warming effects has prevailed with respect to the cooling effects. So now, what can be a problem if we consider what are the effects of climate and air quality policies? So we have seen earlier that air quality policies, due to the short lifetime of the compounds involved, can produce effects on the short life time frame. So we have already seen in developed countries that our quality policies are effective, and so the levels of several pollutants are decreasing in a quite fast way. So that means that the cooling effects of particulate matter, that is a pollutant, and this cooling effect is quite well represented by the particulate matter that is covering the Po Valley, as you can see from this satellite image on the right. So as I said, this cooling effect is likely to decrease quite fast. That means that the masking effect of particulate will decrease as well, and we can expect a faster warming of the atmosphere. So since the climate policy temporal horizon is longer than 50 years, this means that it will not be able to contrast the fast warming that we are expecting in the next decades due to the decrease of PM levels. So that is the reason why science and policies have focused their attention on the role of short-lived climate forcers, so agents that are able to affect the climate in a shorter time frame. This infographic, also from the latest IPCC report, report these forcers in orange, those that have a warming effects, and in blue, those that have a cooling effects with emission sources, anthropogenic emission sources, their lifetime, and also the relative contribution to the warming or the cooling that is represented by the dimension of the globe. So we can see that the blue component, that is the cooling, is quite huge, and we have seen that this is likely to decrease fast in the next decades. So we have seen that the climate policies have a very long time frame, will be affecting in a long time frame, and so what we have to fight this faster warming that we expect, we have to work on species that have lifetimes that are the same order of magnitude of the cooling particulate matter, so that we can have faster effects with those that are expecting only reducing CO2. And these species are, for example, some short-lived hydrofluorocarbons, the black carbon that I have already mentioned, ozone, and here we see also methane. We can't really define methane as a pollutant or a very short-lived compound, because it has a lifetime of 12 years that allow methane to be distributed all over the globe. But nevertheless, we have to consider that methane is much short-lived with respect to CO2, and also that methane has a very important role in the budget of a short-lived climate forcers, stronger climate forcers, that is ozone. In the next slide, I'll try to explain how this works. So I've already said that our quality policies have been effective, and you can see here, for example, how NO2 concentration, NO2 is a pollutant, are decreasing over the last 30 years. This is the example of the UK. But in the same time frame, we see that we don't have any decrease in another important pollutant, ozone, whose precursors, NO2 and volatile organic compounds, are regulated under quality directives, and concentration are actually decreasing over the year. This because beside NO2 and the reactive volatile organic compounds, an important precursor of tropospheric ozone at the global scale is the greenhouse gas methane. Methane that, as is well known, is steadily increasing in the global atmosphere, thus affecting the background concentration of ozone whose atmospheric level are not decreasing at all. So that has been a very brief introduction, and I'm sure that 15 minutes are not sufficient to explain in details what are all the processes that are underlying these important environmental challenges. But I hope that I've been able to transmit these messages that climate change and our quality are closely linked, especially because many of the human activities that are emitting long-lived greenhouse gases are also emitting reactive air pollutants, and many of these pollutants are also short-lived climate forcers. So we have seen that some options for improving air quality can also serve to limit climate change, and vice versa, but it's also true that some option for improving air quality can cause additional climate warming, like, for example, the decrease in the cooling particulate matter, and again, vice versa. So when we think about integrated policies that must be implemented in the future to tackle both challenges, we have to take in account wins-wins and trade-offs. So one good example of a win-win strategy is the global methane pledge that has been announced at COP26 that is addressing especially methane. In this way, we will protect the planet from the climate warming, because methane is a powerful greenhouse gas, much more powerful than CO2, but at the same time will also improve air quality due to the role of methane as precursor of the harmful pollutants and also greenhouse gas ozone. So with this, I conclude. I thank you for the attention, and I will give the floor to Michela Gallo that will talk about methods for accounting emissions.
Okay, thank you, Michela.
Okay, I'll stop sharing.
Okay, can you see my screen?
Yes.
Okay, hi to everybody. You're welcome. I'm very happy for this meeting today. And today I will try to introduce you in a very short way. We have not so much time to the methodologies for greenhouse gases calculation and accounting. So when we talk about methodology, the first point, sorry, I try to, okay, so you can see. The first point is to define who provide this methodology. As you know, I suppose that you know what is the United Nations Framework Convention on Climate Change, the UNFCCC. that was adopted in 1992 with the Quarter of the United Nations, and then the signature for ratification of this convention was opened at Rio in June 1992. This convention entered in force in 1994 when we obtained the 50th instrument of ratification, accept and approval or accession, because the different countries had many type of tool in order to confirm this convention or to assess to this convention. Nowadays, as you know, we have almost 200 countries, 197 countries that ratified this convention. So this is the place where we define the common methodologies and the common standards. I suppose that you know also what is a COP. It's the Conference of Parties. A party is a country, of course, and so is the place where we define annually the general agreement, for example, the Paris Agreement, before the Paris Agreement, the Kyoto Protocol, also the target, the limit of emission, and all the measures in order to contain the climate change. One of the key tasks of a Conference of Parties is to review the national communication of each country and the initial inventories of each country that are submitted by the parties. So as you can understand, the first question is how we can provide inventories if we don't provide before a common methodology for calculate these inventories. The problem started when the Kyoto Protocol was signed and entered in force in February of 2005. In this case, the parties involved were 192. And also in this case, the Kyoto Protocol defined a strong commitment to the industrialized countries to limit and reduce the greenhouse gases. So for the first time, it put a limit to the emission. So I suppose that you remember how the protocols, the information provided by the Kyoto Protocols, it divided the countries in two main groups, the Annex 1 parties, including more or less all the industrialized countries, and the non-Annex 1 parties, constituted by the developing country in general, all the countries more vulnerable to the climate change. So for the Annex 1 party, the Kyoto Protocol define, of course, the limit to emission and a particular performance to be reached. So in 2006, when entered in force this limitation, the situation was the one presented in the slide. So more than half of the total emission, of global emission, was due to countries, China and USA. And it's the same, of course, also nowadays. The target defined by the Kyoto Protocol was not so ambitious because it was a sort of pilot project. It was set a general target of a reduction of 5% of the average greenhouse gases emission reduction compared to a baseline year that was commonly defined the 1990. It was defined also, just another information, another important aspect of the Kyoto Protocol, it was this assigned amount for each party. So this initial quantity, this initial assigned amount, but was called assigned amount units. So each unit represent an allowance to emit 1 metric ton of carbon dioxide equivalent. So one allowance for a country is permission to emit 1 ton of carbon dioxide equivalent. So as you can understand, it's important also from a technical, from a scientific, but also from a legal point of view to define the same quantity. Because as you know, CO2, greenhouse gases are now also an economic value. So we need to be sure that we are talking about the same quantity. During the COP, generally are defined, of course, and it was defined also in the context of the Kyoto Protocol, and after in the Paris Agreement, the list, of course, of greenhouse gases related to this allowance, and also the sector, the general sectors and activity involved in the system boundaries of this application. So another aspect from a legal point of view in the application of a protocol, the Kyoto Protocol, but also for the Paris agreements is the same. This agreement generally permits to group different countries. So for example, Italy is not a party at COP. Europe is a party. And then Europe divide as a sort of subdivision of a target between the different European countries. So in this slide, you can see, for example, the partition of the objective starting from 100% and the general reduction of 80% for Europe between the different European countries. So the general target define also an exact national cap of greenhouse gases for each country. So starting from this general description of what happens during the conference of parties, the agreement, the general protocols and agreements that are signed and commonly defined by all the countries, you understand that we, starting from the definition of national emission of greenhouse gases, so the national inventories, when generally we define a baseline, so something to be compared to the actual level of emission, and then we define a target of reduction that generally is defined in percentage. Okay, so for example, the Kyoto Protocol said 8% for all Europe compared to 1990. So the question is, and is the purpose of my presentation today is how we can measure 1 metric ton of CO2, why we are sure we are talking about the same quantity, and how we can define common and standardized methodologies. So for example, we could use a direct measure of CO2, more or less the same we are doing for other type of pollutant, for example, the particulate, the emission of other type of oxides at the chimney, for example, the production plant. Instead, in this case, the greenhouse gases emission are calculated, are not directly measure. So we calculate the CO2 emitted or related to, for example, an inventory for a country, but also for a single industry or for a product. Why we calculate and we don't measure during, we don't measure the CO2 in order to provide this information, for example, for the national inventories. The reason is that the direct measurement of the CO2 is not considered a reliable and a sufficiently precise measure. And so in order to define the same metric ton, we have defined a common methodology for the calculation. So, for example, of course, we have to consider every time of a general context we are moving, where we are moving. Today, I'll present to you the European emission trading system. In this case, the methodology is proposed by the European Commission. And so the first step you have to do in order to create your inventory, as you can see in the slide, for example, for a factory, you have just to list all the emission sources, 1, 2, 3, and so on. You have to divide it between combustion emission and process emission. So the combustion emission are related to all the exothermic reaction between fuel and the oxygen. So it's just a combustion. When you use, for example, your natural gas for providing electricity to a plant, okay, or a process emission. In this case, is related to a chemical reaction where we consume a quantity of material, for example, carbonate, and it, after a chemical reaction, it produces CO2. When you have the total list of your sources, you need to acquire these parameters, the one listed in the slide. So, for example, in the cases of a combustion emission, you need the quantity of the consumed fuel, the calorific value of this fuel, the emission factor, and the oxidation factor. In case of a process emission, you need the quantity of a material consumed, the emission factor, and the combustion factor. Consider that the oxidation factor in green and the combustion factor generally are set equal to 1, because more or less in all the commonly defined system, these two factors are set equal to 1 in a conservative way, because we suppose that all the material is oxidized or converted in greenhouse gases from a stoichiometric point of view, of course. When we applied, for example, the European emission trading system, so the parameters needed are the one listed, and the formula to be used is a simple multiplication. So if you want to calculate the emission of CO2e, you need just to have your product between fuel in terms of quantity, so tons, for example, or coke, or cube meters of natural gas, standard cube meters, and so on, per the net calorific value, per the emission factor, and if different from 1, also per your oxidation factor. In case of, for example, of a process emission, you need just 3 data in the formula for calculating your emission. So the quantity of material that is used, A, per the emission factor and per the combustion factor. So the type of calculation is very simple, as you can see. So the third question is, okay, I have, it's clear the parameters needed. It's clear the formula to be used, where I can find the values. So the values generally I provided by the national or international competent bodies. So, for example, this is a list using the European emission trading system for the emission factors to be used for the process emission. So, for the calculation, you need to know how much carbonates you consume, for example, 3 tons per 0.44 emission factor, considering the conversion factor equal to 1. Okay. This is an example of list of provided emission factor for the European emission trading system in case of combustion processes. So in case you need to calculate by using the formula for the emission due to the combustion, you can use some international standard factors that are provided by the IPCC 2006. In this case, in the slide, you can find some values used for the oil, for gasoline, for gas, and so on. And so you can have all the values for your calculation, the emission factor, EF, and also the net calorific value in case of combustion, okay? You can use also some national value. So in the context, for example, the European emission trading system, every year our national authorities, but it's the same in Italy, in France, in Belgium, and so on, provide some national value for references for the calculation. So in the slide, it's in Italian because it's an extract of our rule. And you can find the value for natural gas, oil, diesel, gasoline, and so on, for the emission factor, for the oxidation factor, and of course, in the last column, the PCI is the net calorific value. Okay, so as you can see, it's important to calculate the metric ton of CO2 in the same way, because it's a value to be exchanged and is something that is commonly defined between different countries in order to talk about the same quantity, okay? So you need a common formula, common parameters, but also someone who provides to you standardized value or common value or recognized value to be used. So just to have a little break, a very short exercise. You can find in this slide for action of every day. I want you to know, I want you to indicate, in your opinion, just by writing in the chat 1, 2, 3, 4, what is, in your opinion, the higher emission between these 4 actions? The annual consumption of electricity at your home, the annual use of your diesel car, and if you change a single device, important device, for example, like a refrigerator at your home, and a fly from Rome to New York and return. So in your opinion, write on chat. And I leave you just 1 minute, and then we will see how to calculate. Okay. Okay. You are a lot. I don't know is the prevalence. I see 1 and 4, more or less 1 or 4 in your opinion. Okay, let's see what happened. Ok, scusate, non mi va avanti più. Ok. Okay. Now I want you to calculate. These are the value provided. These are international value. In case of electricity consumption, I supposed about 3,000 kilowatt per hour is the average consumption for a family in Italy, generally of 3 persons. And this is the emission factor. In case of use of a car, I suppose a diesel and about 20,000 kilometers. And this is the emission factor per kilometer per passenger. This is a general emission factor for this type of a device and with a weight of about 100. And this is the distance between Rome and New York and the emission factor of an intercontinental flight. Okay, let's try to do your exercise at home. I'll leave you some minutes. 3 minutes, no more. It's a multiplication. Yeah. Also, not a scientific degree, also lawyer can do it. I'll give you just 2 minutes, okay? I check your answer in meanwhile. Okay, so it's not so difficult because in case one is just a simple multiplication, in the second also because the emission factor is in terms of kilogram of CO2 per kilometer. The only problem is to consider in the fourth, it's a return flight, so you have to double the distance. So it's the only trap. Okay, let's see the result. So the winner is the use of your diesel car. Okay, checking your answer. You don't have a prevalence of 2, 1 or 4, 1 or 4. No, the winner is the use of your car. But consider that if you travel by an intercontinental flight more than 3 times, probably you you overcome the final result of your annual use of a car. So you have to consider, of course, that there are some things that we can do in a continuous way, for example, the electricity consumption, or we can do once, but with an high impact, okay? So for example, it's quite high, the impact or the change of your refrigerator, but you probably change it every 5, 6, or 10 years, okay? So it's enough, it's a high quantity. How we can have appreciate what is a 1 ton of CO2 and understand the impact of the things that we do normally during our life. As you can see in the slide, probably the most impacting things you are doing is to use your private car. But consider that 4 ton is a very, how can I say, low emission, because if we consider the emission trading system, we can have some power plant production with an emission of greenhouse gases that is higher than 1 million ton of CO2, okay? Another important consideration is that just one of these options is a direct emission, and is the number 2, the use of your car, because you produce CO2 and greenhouse gases in generally car in that moment, in that place. The other 3 option generates CO2 by it's produced by other plant, other situation in another place. In a place where you produce a device, where you produce a refrigerator, is produced by the company owner of a flight or by the power production plant, okay? So I ask you to, if there are any question, because I have to leave by 1. And so if there are any question about my presentation, I prefer if you can do it now. Okay.
Maybe Michaela, there will be question on the chat and you can reply afterwards.
Okay. Okay.
I think it will be like that. Mario, you say that the chat will be saved.
Yes, exactly. So what we could do is to collect all the questions, and probably at the end of these 2 weeks of webinars, once we have all the questions, we can try to sort of build a FAQ session with all these questions and answers. And this
I have 2 questions and they are very short, so I think I can answer.
Go ahead.
One is, do emission factor include indirect emission? It depends. In case of emission trading, no, it's a direct emission. For the European emission trading is just a direct emission. In case, for example, of my example, so for example, the emission factor for the refrigerator, it includes, of course, also indirect emission. The other question, so you have to check your emission factor, the emission factor you use, what does it includes, of course. What about the direct emission of greenhouse gases from flight before departure, up in the air and landing? Sorry, no, there is another question. Sorry, before. Are different formulas needed to calculate the greenhouse gases emission from different scope? The formula generally is more or less a consumption, okay, per an emission factor. And in case of combustion, there is always more or less a net calorific value. So the formula is not so different system per system. What can change are the value to be used, because different standard can use different databases, different sources, different common standards. For example, in Italy, we use the national value for the emission trading provided every year, and they are different from the one provided by the France in every year for the producer, okay? So, sorry, but I have to do for another exam at 1. And so for the other question, I will provide an answer after the meeting. Thank you.
You will provide the question afterwards. So now I give the floor to Federico Pulselli, that is going to talk about environmental accounting. Federico, you can share your screen.
Michaela, good morning, Mario. Good morning. Good morning, everyone. Can you hear me?
Yes, very well.
Okay. I'm trying to share my screen. Can you see the screen as well?
Yes, very well.
Okay. Okay. I think I have 10 minutes or something more, because we are approaching lunchtime. So I will be fast to give you a basic introduction of the concept of environmental accounting in general, without describing any technical process. I would like to give you something about reasons and implication of the environmental accounting, the various environmental accounting systems, and the need we have to implement that more and more. I would like to start with a phrase from an economist, an important environmental economist, who is Charles Perrings, formerly from the University of York in UK, and then Professor Emeritus at Arizona State University, who at the end of the 80s provided a book called Economy and Environment, in which he stated that the human economy is a physical system of production organized according to a social system of signals. It is very important that he is one of the main promoters of environmental economics and ecological economics as well. But what I would like to highlight from this phrase is the fact that is a question: to what extent we are able to represent a physical system of production in terms of a social system of signals. In this case, the social system of signals is the system of prices. And the question is, to what extent the system of price can embody and represent in depth any physical evidence. For this reason, the rationale I would like to start starts from the concept of environment. What is environment? The word environment is commonly used to identify the natural world, nature, green things, but it has many different applications depending on different disciplines, for example, biology, geology, chemistry, computer science, and so on and so forth. But from an etymological viewpoint, the word environment derived from the ancient French environ, that means to surround, and the same word in Latin languages like Italian, Spanish, and Portuguese, ambient, derives from the verb ambire, Latin verb ambire, that means again to go around and to surround. It emerged from this representation that the environment is something related to the context. And we are not isolated systems, but continuously in connection with the context in which we live. And this is an adage that fed different scientists and different disciplines. Just think at, for example, the evolutionary thermodynamics, like Harold Morowitz, who said that it is not energy per se that makes life possible, but the flow of energy through the system. That means that every system must be connected with something else. Or also Edgar Morin, who said that there's no, that cannot be autonomy without dependence. That seems a contradiction, but in fact it means that any process of self-determination depends on the fact that we are able to extract matter and energy from something else for our survival. To extend this kind of approach, we can mention the concept of sustainability, because sustainability is an opportunity to talk about humankind and human actions, because nature is sustainable. We don't need the concept of sustainability applied to nature. And in particular, the study of sustainability is the study of the relation between human activity and the context in which the human activity occurs. So and the context can be very variegated. The sustainability science is the discipline of the study of the context in a sense. And the context in which we operate, in which human activity occurs, is very variegated. It can be environmental context, our relationship with resources, social, the relationship between persons, between communities, economic, the relationship between and with economic subject, and our relation with money, for example, political relationship within institution, urban, what is our relation with the cities in which we live, and juridical as well. What is the relationship we have with the rules we adopt to live together? In this sense, in order to understand all these aspects, all this relationship, we need different tools with different measure instruments that must be melted together and make complementary with each other. In this sense, the environmental accounting in particular is an ensemble of tools that makes possible to operationalize the concept of sustainability. Composition of the concept of sustainability under this point of view justify the fact that we can represent the concept by means of the three traditional spheres that characterize the concept itself: the environmental, the social, and the economic sphere. Each one needs a kind of interpretation, and we need to put them together. On the bottom right of the slide, you can find a kind of representation of sustainability as the pyramid, in which we can see that the environment is not only the basis upon which the society and then the economy is based, but also the first thing we must consider, if we read the graph from left to right, we must consider in order to have a healthy society that in turn produces economy. At the same time, society and economy produce feedbacks on society itself and on the environment, and we must consider these as well, because without considering that, we are not aware of what is happening to the first stadium of our life, of our development, and we can damage the basis upon which also the economic system is based. In this sense, the systems of environmental accounting based on different unit of measure other than the economic financial one can give us a lot of information that is complementary with respect to the economic one, and give us the possibility to make less and less mistake in our choices. Now I can give you some examples, an implication of application of environmental accounting system. The first one is the one that Michela has just, Michela Gallo, Professoressa Michela Gallo has just described to you, the greenhouse gas inventory according to the guidelines of the IPCC. I would like to present to you an experiment we have been doing in our province, in the province of Siena, in Tuscany, for 14 years. And every year we renew the greenhouse gas inventory in order to have a systematic monitoring of greenhouse gas of the area. This systematic monitoring has a couple of consequences. The first one is a great capital of information that can be used to make policies. And the second one is the fact that the province achieved the status of carbon neutrality in 2011. This is a status that has been also partially certified 1464, according to the ISO 1464 standard. It follows the IPCC guidelines, and every year we provide from zero the inventory. This is more or less the result. The most important thing is that at the beginning we didn't have the status of carbon neutrality achieved. After the first results, the political body assumed the responsibility to make policies according to the results of the method, and they contribute strongly to achieve the results of the carbon neutrality status in 2001. On the basis and by virtue of some policies based on energy savings, the control of private heating system, the use of incentive for renewable energy, a more and more precise waste management and careful waste management, communication and dissemination, preservation of forestal ecosystem, action in the public transport, so that this procedure became a governance experience, because the system of environmental accounting fed the policies in order to achieve an important result that we are trying to communicate more and more to the population. Another important result of this application, multi-year application in the province of Siena, is the creation of a kind of organization that is called Territorial Alliance for Carbon Neutrality. communicating the results of the GHG inventory, we are trying to involve different components of the society, organization, enterprises, companies, associations, schools, single persons, in order to create an alliance and contribute better and better results every year. Different systems of environmental accounting may bring about different results. This is an example. You can, for example, calculate the CO2 or the greenhouse gas embodied in trade. If we consume a good that is produced elsewhere, in a sense, we can assume the responsibility of the demand we express and consequently of the emission that is the greenhouse gas emission that is generated in the place in which the product is produced. And this changes the geography of the emission all around the world. We can see a couple of examples, a global example involving especially China and other countries, and a focus on the Mediterranean, of the Mediterranean region. The environmental accounting can give a lot of results that are complementary with the economic ones, and a lot of implication can be treated from that. Another important results, very well known worldwide, is the overshoot day, and the environmental accounting system on the basis of the overshoot day, as you know perfectly, is the ecological footprint. That is a translation of our consumption into land, into the capacity of the ecosystem to produce resources. The last example I would like to propose to you, as we are approaching, as I said before, lunchtime, is the one of a menu. The picture you can see on the right. It is a menu, a restaurant menu, and it is a list of pizza receipts. The only peculiarity of this menu is that we added a column on the right, a column made of signals represented by small suns, the yellow suns and the black sun. How much sun is embodied in the receipt we are eating? How much sun is embodied in food? The yellow sun is the renewable sun, sunlight, rain, atmospheric things, geothermal heat, and so on and so forth. The black sun is the non-renewable sun, fossil fuel, I don't know, organic substance exploited too fast in the land, chemical fertilizer, etc. All these things can be accounted for in a system of environmental accounting that is called energy evaluation. Energy spelled with an M. It is not a mistake, an M, like in Madrid. The result was pretty surprising because the customers, even without knowing what was the deep meaning of energy and the deep meaning of the presence of sun in the menu, changed their choices. That means that the information that is embodied in a system of environmental accounting can bring about results, important results, also in terms of our own behavior, daily behavior. As it is a little bit difficult to explain, though it is a very fascinating concept, it is a little bit difficult to explain how it is possible to account for the sound embodied in stuff. I would like to propose to you a comic book we produced just in order to explain this kind of context of concept. And you can find it on the internet. You can download it for free. And if you have obviously questions now about the presentation, in the future about the comics, I'm here for you. I think I conclude my presentation. Thank you very much for your attention.
Okay, thank you, Federico. I don't know, Mario, what would you like to do? Are we accepting questions?
I think we went a little bit beyond the schedule, so we could probably take just one quick question to conclude, and then we'll keep track of all the questions in the chat box.
In the chat, okay.
And we'll try to use as best as possible the questions in the chat. We will probably fill a simple document with the answers to those questions. So if there is a quick question, I don't see any hand raised. So we are all starving.
The first question is why the pizza with the tuna and capra is so pollutant?
Yeah, that's a very common question. And it's one of the main results that they highlighted in the restaurant, because it is also one of the most requested pizzas in that restaurant. Tuna is on the top of the trophic chain. So in order to obtain 1 gram of tuna, you need a lot of steps behind in order to obtain that. So tuna per se is beyond being a scarce resource, is very expensive in terms of the sun requested to produce 1 unit of product. So that's the reason why that pizza was very impacting.
Okay, so I think that as Mario suggested, we can collect questions to all the presentation of the session and we will reply in the next few days.
Yes.
So I think that we can conclude the morning session and see you again in an hour.
No, at 3 p.m. At 3
3
p.m.
p.m.
So let
okay.
me remind you. Yeah, let me remind you that we will distribute the recording of these webinars. I'll send you the link right after the end of each module. And let me remind you also that this afternoon at 5 p.m. after the conclusion of the second part of this webinar, you will have a short learning test of 50 minutes of duration as a webinar, and that is important also to evaluate ourselves as speakers. So please complete that quiz as soon as possible. So I don't see any other hand raised, so we can meet this afternoon at 3 p.m. The link is the same, and also the YouTube channel is the same. I'll stop the recording here and see you this afternoon. Bye to everybody.
Bye.
See you soon.
Thank
Bye.
you.
Bye.
Thank you. Bye-bye.
Bye. Thank you. Thanks indeed
Bye.
to all the speakers. Bye.
Bye to everybody. Goodbye.
Welcome back. Hello to everybody. We will start in 5 minutes. So if you want to, in the meantime, switch on your camera, take your seat, have a coffee. Ciao Federica, ciao Elisa, ciao Stefania. Hello to everybody. I've already started the YouTube streaming. While we are talking, we will send you the. Actually, I will put all the links to the recordings in just one document, and send to you the link to this Google Doc document. So you will have all the links together at the end of these 2 weeks. You can save the links. You can actually also download the recording of the webinars, depending how much space you want to use on your computer. Remember that the links to be open needs a passcode, so be sure also to copy the passcode for the recording, okay? How are you? What do you think? Is it useful, this sort of webinar? Federica, Stefania, Matteo, Giorgio, Ivan. Do you find yes, useful?
Yes, it's interesting.
Is the level, yeah?
But to be honest, I think that at the end of the day, my mind will be
explode.
Yeah, but I think that for you it's the same. Because we have to hear, but
yeah, you're right. You're right. Yeah, there are many topics altogether in the webinar are very dense of information. That's why probably the recordings are useful, but you know, it's just for 4 hours per day. So I hope you can survive.
Yeah.
Yeah, these 2 weeks are a sort of, you know, general introduction, a very broad overview of all the topics, all the questions related with our PhD. But of course, we need time to digest, time to go deeper, you know, in these topics.
Yeah, but I think that this reaction, my personal reaction, it's related also that we are distance. So yeah, it's completely different from the kickoff from Rome, the atmosphere, and see you in presence.
Yeah, you're right.
Not compare.
Yeah. So I see that, I don't know why, but Alessandro, you are now the organizer, Alessandro Bigi. Alessandro, can you pass me the host of the meeting? Because I do not have all the functions. I don't know why now you are the organizer. Unless you want to be the organizer, you need just to see if there are noises, if there are some warnings during the meeting. Alessandro, are you connected? Probably Alessandro is not yet at the computer. Okay, we are rapidly increasing. 45. This morning we reached 147 persons connected. Alessandro, ciao. You are the host, the organizer of this meeting. If you want to be, okay. I mean, I don't know. It was automatically like that.
Yeah, exactly. I found out. I thought it was a mistake.
It's okay. It's okay. I mean, if you want to pass me the host, otherwise you can.
Yes, I think it's better. Yeah. Just
you have to go on my name.
Yeah, thanks.
More, and then
yep.
Okay, yeah, okay.
Yeah, pardon.
Yeah, if there are problems with YouTube, all these things, I will, without interrupting, I'll try to intervene. Okay, it's 3 p.m. and I see already most of the speakers and many students. We'll wait another 2 minutes, and then I'll start again the registration. Claudia, are you going to present the speakers, or are they presenting themselves?
I think themselves, but I'm here, so no problem about that. But I think Marco could be chair of the session.
Ah, okay, Marco. Okay, let me project just the program of this afternoon. You see that we have 2 slots. One on climate models, tools for studying processes and making predictions, and one on impacts and adaptation. 3 speakers for the first one, Marco Gaetani, Roberto Buizza, Giorgio Fosser, and then 5 speakers, Soldati, Flandoli, Neri, Godio, and Marani for impacts and adaptation. As before, if we do not have time to go to answer to all the questions. However, you will have a very short time at the end of each presentation for some questions. But if we run out of time, please write your questions in the chat, because we save the chat and we will share with everybody together with some answers. I think we can start the recording. Okay, good afternoon to everybody. I pass the floor to Marco. So Marco, if you want to introduce the afternoon session, please go ahead.
Yes. Thank you, Mario. Thank you all to all the attendees. I'm going to share my screen. Okay, can you see the screen?
Yes.
Okay, I put it in presentation mode. Okay, is it the correct view?
No, we
okay.
are. Yeah.
Yeah, I know. I change the share, which is this one. Okay, now it should be okay.
Yes, thank you. Please.
You're welcome. Okay, so thank you, everybody. So I'm going to talk about in this slot. We are going to talk about the climate models that we have been mentioning a lot of times during this morning, that you heard about many times, for sure, when we speak about climate change. And we will describe these, which are basically tools we use for studying the climate system and for making prediction. I will start. This is the agenda for this hour. I will start giving you an overview of the first climate models we know from the history, which have been used for simply for a simple estimation of the global mean temperature. Before to start, I want to give you a few definition, a couple of basic definitions that can be useful for understanding this lecture. So first, I want to define what a dynamical system is. A dynamical system is a physical system simply evolving in time. And a model is basically a set of equation or a law describing the state and evolution of a dynamical system. So basically a model is something that we use for describing the system. It's not the system itself. So we have to know that a model is a representation of reality, is not reality itself. And this brings with the itself, of course, all the limitations of that can be applied to any model. So the main ingredients of a model in general is a law, so an equation describing the evolution of the system, the forcing, which is basically the driver of the evolution, basically what gives the system the energy to evolve. But because we speak about evolution, so we mean that we need an initial state, we need the initial conditions for this evolution, because each step of in time of the evolution depends on the previous step. And of course, we have to give the boundary condition to the model for the system to evolve. So the constraints of the model. And then after we give all these ingredients to our model, we can describe the evolution of any system. And so climate, of course, is a dynamical system because climate evolves in time. And what is the driver? The main driver of the climate system is the solar radiation, coming from the sun. So I'm going to describe the simplest model that have been already introduced by Professor Zardi this morning, that we use to describe, to estimate the global average temperature on Earth. So basically, this is like a simple description of the model. Basically, we have solar incident radiation, which it hits the surface. This is at a short wave. This heat input that we have into the system is balanced by heat loss to space through infrared radiation, which is basically thermal radiation. So the temperature at the surface is depends on the balance between short wave and infrared radiation. This balance is described by the Stefan Boltzmann law, basically, which this is the balance in which S is the solar radiation, and this accounts for the thermal radiation we emitted to space, and this is temperature. This is the Stefan Boltzmann constant. This basically constitutes. This is what we call a zero dimension global climate model. This is the simplest model you can find, and of course, in this equation, we have the forcing, which is the solar radiation, and then we have the predictant, so the quantity we want to predict. This model has no, because we want to predict the global mean state at the equilibrium, so the equilibrium between shortwave and infrared radiation. We don't need initial condition in this case. But we need the boundaries, and the boundaries for these problems are, for instance, the geometry of the problem, because we know that the incoming shortwave, the incoming solar radiation is the flux of the incoming shortwave radiation is the solar constant, which is 1,366 watt per square meter, which basically hit the cross section of Earth, which is given by this expression. This is the surface of the circle. And then we need also to take into account the fact that 30% of this radiation is is reflected to space. And this quantity is what we call the albedo, so the radiation which is reflected. And then we have to consider that, so we take this into account in this part of the equation. We have to also account for the fact that the infrared radiation is emitted on the surface of a sphere, which is, and this is the surface of the sphere with R is the radius of Earth. And then we also need to take into account the effect of greenhouse gases. This is a schematics for the radiative balance at the surface of Earth and into the atmosphere with the incoming solar radiation which is reflected. And also this is what happens when the infrared radiation interact with greenhouse gases. So part of the infrared radiation is a small part is emitted directly to space, but most of the infrared radiation interacts with greenhouse gases, which re-emit infrared radiation to the space, but also towards the surface. And this is what basically keep warm the Earth surface. So basically, if you take all these elements into account, and then you can write, you can so put all these boundaries into the equation. So taking into account the forcing, the solar forcing, that is the solar constant, all the elements. A, this is the albedo. This is the emissivity of Earth. So the effective emissivity to space, which means that this coefficient means that only 60, this is the fraction of the solar radiation which is actually absorbed by the atmosphere. And then, so if you make the computation, as you already saw in this morning, you get the correct estimation for the thermal equilibrium of the atmosphere, which is 15 degrees on average. So this is basically the definition of a zero-dimension global climate model with all the components. The model is the Stefan-Boltzmann law, the solar radiation is the forcing, geometry, albedo, and emissivity are the boundaries, and the temperature is the predictant. In this case, is not evolving. This is a quite old model, because this is something that we know since a lot of time, because the first one who used this model, who basically found the link between the CO2, in this case, a specific greenhouse gas, the CO2 concentration into the atmosphere and the warming of the atmosphere, was Svante Arrhenius in 1896, who basically was the first model for the greenhouse effect. And using this simple law, he could predict the global warming resulting from increasing CO2, and also defined what this quantity, which is very important when we speak about prediction for climate change, which is climate sensitivity. Basically, the climate sensitivity is defined as the temperature increase we expect for doubling the CO2 concentration into the atmosphere. And this is a table with different concentration of CO2 in the atmosphere. 2 stands for double concentration compared to pre-industrial values, for instance, and Arrhenius could estimate the climate sensitivity, the increase in temperature, into 5.5 degrees. But I mean, if you take, so what's the consequence of heating the surface of the planet? You already saw this plot. The fact is that temperature decreases with altitude because it's warmer close to the surface and it cools in the upper level. But if you only take into account the effect of the greenhouse gases, so the radiative cooling from the greenhouse gases, so basically if you only use the Arrhenius model, this lapse rate is 15 Celsius per kilometer, which is actually quite different from what we observed in the real atmosphere, which is basically 6 Celsius per kilometer. Why this difference? Because basically the zero-dimension model, the Arrhenius model, doesn't take into account the heat transfer in the vertical direction by convective motions. Actually, this is the part. This is a part of the radiative balance that I didn't mention in the slide before, because basically this is most of the infrared radiation is the cooling of the surface is through the emission of infrared radiation, but part of this cooling is also accounted by convective motion, dry motion, but especially by moist convection. Basically, if you heat the surface, the surface cools via evaporation, and eventually this evaporation, this water vapor, which basically is transported upwards, condensate and release the latent heat. So the result is that basically the warming at the surface is redistributed along the atmospheric column. And this was basically the the contribution of Syukuro Manabe to the improvement of the model of the radiative balance of Earth atmosphere, because during in two works in two papers between 1961 and 1975, he could improve the model, the simple model, taking into account the role of convection, as we saw, and the water cycle in the Earth radiative balance. So basically, the role in convection, in moist convection, in redistributing through evaporation and condensation the heat along the Earth atmosphere. And this is the reason why he was awarded, so Syukuro Manabe and Karl Hasselmann were awarded with the Nobel Prize for Physics in 2020. Together with Giorgio Parisi, he was awarded for his contribution to the general understanding of dynamic system. Another contribution, so using this approach, this improvement of the radiative model of Earth atmosphere, Syukuro Manabe could also make a better estimation of climate sensitivity. So he basically provided new constraints to climate sensitivity. And in these two papers, so in 1976 and 1966, 67 and 75, he could estimate the climate sensitivity. So the increase in temperature when you double the CO2 concentration between 2.3 and 2.9, which is a bit low compared to the estimation by Arrhenius, who used a very simplified model, but which is very close to the estimation of climate sensitivity that we get from the IPCC, the last IPCC report, which is between 2.5 and 4. You can see this basically in this plot, in which you see the profile of the vertical profile of the atmosphere. You can see that basically if you double from 300 part per million CO2 concentration to 600, you see this increase in temperature between 15, which is the global average, towards 19 in this case. Of course, these models I've been describing here are very simple. These are very good in predicting and in estimating what, the global average temperature. Of course, if you want describe and simulate and predict the evolution of the climate system at a finer resolution, at the finer scale, you need a much more complex model, which is basically what we call a climate model, in which you solve all the equations describing the system, the climate system at each grid point, so over the surface and in the atmosphere, at different levels in the atmosphere and at different levels on the ocean, to see the evolution, to describe the evolution of the system. Of course, you need to give the forcing again, which is the solar radiation, but also the interaction between all the components of the climate system. And also you need an accurate description of the initial state and the boundary condition, which are, for instance, can be land masses, orography, and ocean, and all the fine characteristic features of the climate system. So I can stop here and leave the floor to Roberto for giving you more details about climate modeling, Earth system modeling in this case. Thank you.
Okay, shall I take it over? Can you hear me?
Yeah? Yes, very well.
Okay, perfect. Thank you, Marco, for a great introduction. So let me just upload my presentation. Can you see it? Yeah?
Yeah, very well.
Okay, very good. So part 2 of this lecture is about the chaotic nature of the climate system and probabilistic climate modeling. What do I mean with that? So the key points that I want to make is that now you have heard that the system is complex, okay? And you know, for example, that these models that Marco briefly mentioned are used also to make weather prediction, and weather prediction fail after a few days, or maybe a few weeks, it depends on the scheme. So how can we take this into consideration? Is there a way that we can estimate the uncertainty in the forecast? Okay, so this is what I want to discuss now. This is a very important subject, because one of the criticisms that the climate skeptics raise to the work we're doing is precisely that one, that models are not perfect, and so why should we trust models? I try to raise this issue also this model, a kind of an epistemological issue. Why should I take a decision today that can affect the life of many people for the next generations based on a model that I know is imperfect? As a suggested reading, I invite you to read Bradley et al., The Philosophy of Climate Science. It's a paper written by Richard, Roman, and others. They are philosophers, but they've been working a long time with physicists, and it provides also to the people without a background in physics and math with a very good introduction of a problem of how we can trust a model. Why should we trust a model? What is a model? Okay, it's a very interesting read also for mathematicians and physicists. Now, Marco mentioned, Marco mentioned the fact that the global models are solved on a finite grid. I just want to say that what is solved is essentially a version of the equation of motions, the equations of Newton. I remind you all that the Newton law, F equal ma, force equal mass times acceleration. If you write this equation for a fluid, and this, more specifically for a fluid on a sphere, on a rotating sphere, you get to this type of equations, okay? They don't look terrible. Indeed, they are not terribly complex, but we cannot solve them analytically. We need to solve them numerically. And actually, there are 3 terms, what I indicated with P, which try to simulate the phenomena that were discussed this morning, for example, the interaction of the ocean with the atmosphere, the interaction of the atmospheric flow with vegetation or with a lensy contrast and so on. So simulating all these phenomena is extremely tricky. We are doing our best, and we try to do it by solving those equations on a finite grid. Okay, this is what is done when we try to make a weather forecast or a climate projection. So the atmosphere, the globe, is seen as a mesh of the small cubes, or with a size which varies depending on the quality and of the resolution of the model. Say for climate models between 50 to 250 kilometers. So you must keep this in mind when you look at climate simulations. The model which is behind this climate projection sees the world as a mesh with 1 point every 50 kilometers. Okay, so it knows nothing about the difference between where you live and the field outside your city, or it doesn't know much about the steepness of a coast between around Italy and so on. It tries its best to simulate all these phenomena, but clearly it doesn't do it precisely. okay? And given that the equations are solved with a final resolution, it has also problems in simulating extreme phenomena, the phenomena that causes the damages. I'm thinking about the hurricanes. Here on the right, you see a hurricane as it is simulated in the European Center model with a resolution of 9 kilometers. This is the global model used in weather prediction with the finest resolution today. Go back to 63 kilometers. This is the resolution of the Earth system models run to generate climate simulation, the best climate model used to generate climate simulations up to 20, 30 years from now, use a resolution of about 60 kilometers or maybe even 100. You see that this type of structure is seen as something much weaker. You can imagine that simulating the winds associated with this structure at 60 kilometers they're not going to be very close to the intensity that you experience if you had experienced if you were in New Orleans when Katrina hit, okay? So point number one, we have an issue of resolution. Point number two, we have an issue of uncertainty in estimating the initial condition of our projections, okay? So the end result is that it's very difficult to make forecast. And the best way to make a forecast, which is what we have been using now to estimate the uncertainty in the forecast, is to use a probabilistic approach. So instead of doing just one forecast, as I was showing in these slides, okay, what we have been developing are systems, methodologies so that we can have a range of possibilities. With a range of possibilities, if we design a probabilistic system in a reliable way, we can use them to estimate not just what is going to be the most likely scenario, in this case, the most likely path of a hurricane, but also the uncertainty around it. So here you see the example of Tropical Storm Sandy that hit New York in 2012. You see that this was a forecast issue on the 23rd of October. A hurricane hit New York on the 30th. So 7-8 days before, there was a range of possible paths of a hurricane. There was a large probability that it was going to hit New York, but there was also some chances that it would stay over the sea. The same type of approach is used when we try to estimate the future climate scenario. So we don't do a single forecast, but we do an ensemble of integrations, and we use them to estimate the probability that different events could occur. Here on the left, you see an example of a 5-year forecast issued by the UK Met Office. You see on the up to the end of this black lines, you see a range of forecasts in red, and in black you see the I think the observed scenario with also an uncertainty around the observed scenario. Here from the blue onward, you see the cone of possible future states from forecast issued on 2020 for the next 5 years. It's a forecast for the global warming, for a global annual temperature. So it's not just one forecast, it's an ensemble of that. On the right, you see something similar from IPCC, where they've been trying to predict the evolution of a global mean temperature for the next 10 years. So forecast, the initial time a forecast issued, not just one, but an ensemble of them. An ensemble generated using different models. In this way, we are trying to take into account the fact that given that we don't know exactly how to simulate processes. We use all the best models available, and we use them to estimate what could happen in the future. Now, and this is, if you want to go even further into the future, these are the cones projection for the global warming, which you find in the latest IPCC report, the assessment report 6, the summary for policymaker, issued in August 2021. So what they report here is a cone of possible warming and cumulative CO2 emissions in a range of emission scenarios, going from scenarios where in the next 50 up to 2050, we manage to reduce emissions in blue, the warming stays below 2 degrees, and there's a certain uncertainty, to the scenario SSD 8.5, where we keep emitting and increasing the emissions as we have done in the past 10 years. We reach in 2050 more than 4,000 gigatons of CO2, of accumulated CO2 equivalent. So this is taking all greenhouse gases into consideration, and we can warm the planet by more than 2 degrees. So these cones, it's essential to try to estimate these cones of uncertainty. And the way it's done is by running ensembles of forecasts. So we are trying to estimate what is the initial uncertainty. We're trying to use different models, and by running them and computing the probability at final time of what will happen, we estimate the future states. Now, how can we, one key aspect of this technique is that it works only if we are able to build a reliable ensemble. So it's not that I can just run models in a kind of a random way. I need to think carefully how I design my ensemble. I need to design them so that they are reliable. What does it mean that I have a reliable ensemble? It means that if I am going to make forecast and my probability that something will happen is 75%, like at this point, then on a perfectly reliable ensemble, if I look at many cases, I should observe that event 75% of the cases. If I issue a forecast with a 50% probability, then I should see it happening 50% of the time. So if I build a diagram like this, where I plot a forecast probability versus the observed frequency of an event, I can see them lying on the diagonal. So an ensemble technique is valuable to generate forecasts that estimate uncertainty only if they are reliable. So they spread the divergence among these different members, reflects the real uncertainty of the system. Okay. Now, you find in my presentation some more slides that describes a little bit more the details. In particular, let me just say that, and let me connect this to the Nobel Prize of last year. So one of the big issues is, how do I simulate model uncertainty in these models? Okay. Well, one way to do it is to design, to include in my equations a stochastic term, which I represented here with a delta F, a stochastic term that tries to take into account the uncertainty of a process. So Giorgio Parisi, for example, did a lot of work, the physicist from La Sapienza, did a lot of work to try to estimate how I should formulate this term to be inserted in my equation, so that when I can generate a reliable ensemble of the future states of the system. So my final comment is the following: the uncertainty in the models is there. We shouldn't hide it, but we should try to estimate it. So up to 30 years ago, in weather prediction, we were issuing one single forecast. We have learned now that it's much better if we estimate the uncertainty in the weather forecast and we issue forecasts in a probabilistic way. A similar approach should be followed with climate projection. Don't hide the fact that the models are not complete. I like to say that the models are adequate to simulate what will happen in the future, and we use them in an ensemble mode so that we can estimate the range of possible future scenarios. So my conclusions: global, coupled, Earth system models aim to simulate all relevant processes in an adequate way. They are not perfect, but they are adequate to be able to understand what will happen in the future. For example, if we don't stop or if we don't reduce emissions. Uncertainty should be hidden, should not be hidden, sorry, not should be hidden, should not be hidden, but must be estimated. And with this, I stop here. Back to you, Marco. Thank you.
Thank you, Roberto. And I leave the floor to Giorgia, who will tell us how models are used for predictions, climate predictions in this case. Thank you.
Hello, everybody. So can you see my screen? Here we are. Can you see it? Yes?
Yes,
yeah.
Thank you. Yes, Giorgia.
Excellent. Sorry. So, okay. Okay, here we are. So as the previous speaker already said, let's start what how the global climate model work in a very simple way. So what they do is the GCM divide the globe into three-dimensional gray boxes or cells, and they represent a specific location and elevation. And all these cells interact with each other, exchanging information, like temperature, humidity, pressure, fluxes. And this interaction goes both horizontally and vertically. And obviously, as you heard before, this model needs some information to start. So they need the initial state with, like, for example, initial temperature. They need some boundary condition to know where, for example, the mountain are, or where, how high they are, where are lakes, and so on. And obviously, they need the forcing, including natural and also greenhouse gases information. And with this, the model is able to evolve and represent climate and or climate change. One small thing that we should clarify is that the model that I use for forecast are the same that I use for climate analysis, but the forecast one introduce also observation to try to keep the model closer to reality. While when we study climate or climate change, this is not included. So it's like we know the forcing for the past, but if we want to investigate climate change, then we need also to know how the forcing will change in the future. And how do we do that? This is like is the IPCC that provide what I call the climate scenario, that are defined as a plausible representation on the future development of emission of greenhouse gases and aerosols, based on a coherent and internally consistent set of assumptions about the driving forces, which are like the demographic and socioeconomic development, technological changes, so energy and land use, and obviously their relationship and how they would affect each other. And so what come up is with representative concentration pathway that you can see here, for example, for carbon dioxide, but is done for all greenhouse gases, and provide how they will change. For example, in this case, CO2 will change up to the end of the century. And as explained before, there are different scenarios. The more optimistic one, and then the worst scenario, that is the RCP 8.5. And obviously, with this information, we can start running a model, like, for example, a GCM model. And I think you already saw this picture many times. There's a global surface temperature change at the end of the century. And you can see that there is a range of possible warming. It goes from 1.4 degrees to 4.4. And we call this span between the option uncertainty that's already introduced by Professor Buizza, And uncertainty are defined with a state of incomplete knowledge that can result from a lack of information or from disagreement about what is known or what is even knowable. There are different sources of uncertainty. Some have been mentioned. I'm just going to mention a few of them. And it's like, obviously, it's climate scenario. You can see it's like the different color. And this is which pathway we choose for in terms of greenhouse gases, for example. Then there is the internal variability. This is linked with the chaotic nature of climate. So the climate is not stable. It will vary over time, even without considering climate change. And then obviously there are models. And these given examples like the reddish color, bank color, would represent the spread in the model. But why the model? The model, because they have to represent a lot of processes. It depends on which process they decide to represent and how they decide to represent. Because as I already mentioned before, the different processes have work on a different time scale and spatial scale. So the GCM have been increasing in spatial resolution over time from the first IPCC report. The CIMIT-3 had the spatial resolution of around 300 kilometers. And now with the last report, the model have more or less 100 kilometer resolution. But even with 100 kilometer resolution, there are processes that cannot be represented or not in reality and in detail. If you think about a box, one of the box of the model, and you think about clouds, obviously they will start developed at a much smaller scale than 100 kilometer. And although they are what is called subgrid, so they still have an impact on the climate. So what's the model need to incorporate these processes, although it doesn't see them, it needs to incorporate them. And how it does that, it does it with the parameterization. The parameterization essentially are an approximation of reality. What the model wants to know is the contribution of this process that it cannot solve, the contribution to the resolved scale. And obviously when you introduce parameterization that are necessary for the model to work, you introduce some uncertainty or some error. And that's why you start having, is one of the reasons why you have this divergence between the models. And to give you another example, it's like on the impact of the resolution. Here you have the orography of Sierra Nevada, and these are the observation. And that's how the orography is represented in the model of 110 kilometers more or less, a 25 kilometer and a 9 kilometer. And you can see that the level of detail is much better when you go for higher resolution. So ideally, you would increase the spatial and the temporal resolution of your GCM, and you would include more and more processes to be able to represent correctly the very complex climate system, Earth system, really. But the problem is when you increase the spatial, the temporal resolution, you kind of simulate more physical process, then you need more computational resources. And then is always a balance. It's a balance on the detail that you need to represent a phenomena and the cost that that has. And you need to choose. There is never a perfect situation, but independent of the purpose, you can choose one thing or the other one. One option to increase spatial and temporal resolution is regional climate models. The regional climate model started in 1980s, and the basic idea behind them was that a GCM, so a global model, would be able to represent the global circulation, so large scale, while the RCM, so the regional model, would be able to refine the information both spatially and temporally, refine this large scale information to account for what happened at sub-GCM grid. And this is because if you think about regional climate, it's always an interaction between what happened at large scale and what happened at the regional scale. So if you think about Italy, so let's imagine there is masses that come from the Atlantic toward Italy. And so the large masses coming from the Atlantic would be like the large scale. But then obviously how the climate develops in the Po Valley depends also on the interaction between those and topography, but also the coastline, the lakes that are there. So it's like is the characteristic of the region that then modulates the climate on a specific place. So what it was found is that to simulate climate and climate change at the regional scale, you would need a higher resolution than a GCM. And to give you like a very simple, how do we do this? So instead of considering dividing the whole globe in boxes, we just focus on a smaller area, a domain, let's say Europe, is still divided into boxes. And this time the boundary conditions are given by the GCM. So the GCM would give information about wind, about temperature, humidity, other variable to the border of this area. And then the RCM will be able to develop solving the same equation, the GCM. So it's the same equation of the GCM, but on a smaller domain with a smaller grid. The thing is that the information obviously flow from the GCM to the RCM, but in most of the case, there is not information flowing from the RCM to the GCM, which also means that the RCM can add information, but they cannot correct any error come from the GCM, or little at least. So if, for example, a GCM is known to be very humid for some reason, then the RCM will have the same problem or similar problem. Here is a quick overview that what could be an example of the definition between, so these are observations. This is mean precipitation in summer. And you can see the impact of the resolution. So the regional model is given much more detail of the precipitation pattern over the Alps compared to a coarser resolution GCM model. So the RCM definitely have some advantages. They definitely can give most of the case a better representation of local processes. They can, so the parameterization that still exists at this resolution can be kind of fixed for the region that we are interested in instead of being valid everywhere in the globe. And they're cheaper to run, so they cost less in terms of computer resources. On the other end, obviously, there are disadvantages because obviously you're focusing only on area and not on the whole globe. There is not this feedback from the regional. So if anything, if the climate is changed by regional characteristic, this cannot impact the global scale because there is not this double interaction. And obviously, as I said before, it depends on what you receive as the input from the GCM and plus other technical stuff. But the RCM and GCM have a series of known limitations that I'm not going to go in detail. But just to give you an example, one is that they struggle in correctly represent subdaily precipitation intensity. They tend to underestimate them quite strongly. And obviously, they have a limited representation of the complex topography, and therefore also the interaction between the land and the atmosphere is simplified. And some of these problems are mainly linked to the spatial resolution. So ideally, if we would increase the spatial resolution, we could solve this problem. But others are mainly linked to the parameterization of convection. What's convection? Why convection is so important? You already heard this vocabulary before. That is one of the dominant source of precipitation in many regions of the world, thinking about Africa or South America. But also in Europe is responsible for heavy, very local, very short-lived precipitation, especially in summer for our region, and is often associated with hail, lightning, and strong winds. And it can lead to flash floods or landslides. So it's a very important process, but the problem with this process is that it starts from a very small scale, so kind of kilometer scale, and it can last just a few hours. So it's in this kind of situation that the GCM and the RCM are difficult in representing because it just don't see it. And so how do we solve the problem? One of the options is this model that are called convection permitting models, CPM. They are kilometer scale models that do not use the parameterization of convection. And they don't use it because on one side, they have a very high resolution, and also because they are different model. They are called non-hydrostatic model. I'm not going to go in detail to that, but they account also for the vertical acceleration that is neglected for regional model because standard one, because it's not important when you are around 10 kilometers and above. They work in the same way than what we saw for the regional model. So they still take information from a GCM, for example, and they focus usually on smaller domain than what is done with the RCM because they are more point because they have a smaller resolution. Or they can use what is called an intermediate nest. So the GCM would provide information to a regional model, then will provide information to a CPM that will be focused on a smaller area. And to give you an idea of what they can do, what's the difference with the standard regional model, this is a Bocastle case study. It was a very strong precipitation on the 16th of August 2004 that created a big flood with devastating results. And this is what the radar catched at 2 o'clock. These are the rainfall rates, hourly rates. And this is how the model simulate that. And you can see that the regional model at 12 kilometers was just unable to catch this pattern, this rain band. While if you look with the convection permitting model at 4 kilometers, you start seeing similar patterns, similar intensity of precipitation. And when you look even higher resolution, 1 kilometer, always with the convection permitting one, you can see that you have a much similar structure to what a standard regional model would be able to do. They are also important when we look at climate change. So these are the changes in future changes in heavy precipitation for the south of UK. In winters, like there is between these two figures, like you can see there are almost no difference. There is no difference between RCM and CPM, but when you look in summer, then you can see that the convection permitting model would show a strong increase in heavy precipitation that is not detected by the standard regional model. So this model could be very useful, although they're not free of error either. But the big advantage is that they have a resolution of, most of them, they use a resolution around 2 kilometers, 2.5 kilometers. And so they can be used also for impact studies. They have some advantages compared to observation, and obviously some disadvantages. So they are spatially uniform, while usually like station are scattered around in uniform way. But on the other end, they are a much coarser resolution, so they cover much larger area than a station. They are not missing dates, but they cover much shorter time scales. So usually a simulation with convection permitting model will span maximum 20 years. Most of them are just 10 years. They are not affected by human error, so no problem with missing measurement or wrong measurement. But on the other end, there are all the model biases, errors. But the main thing is that they can provide physically sound future projection, which observation cannot do. And I'm going to leave you with a nice video that usually people like. This is like a simulation over Africa with a global model at 25 kilometers and with the convection permitting models at 4.5 kilometers. And you can see that the precipitation that is in colored is much more scattered and much more strong. You see it's often around red. And give you an idea how the two models represent precipitation. And the main point that I wanted to make is that when you investigate climate or climate change, there is not only one model and not even one type of model. So, and choosing one or another one, it depends on the purpose that you want to look at, what you want to look at, what's your purpose. And that's what drives your choice at the beginning. And with this, I I'm done.
Thank you, Georgia. So I'm sharing now. So I think that we have 5 minutes for a couple of questions or more, if these questions are quick. There are some questions in the chat. What I'm supposed to do with that? I mean, I will give the priority to direct questions there. If there are no questions, I can try to respond to or we can try to respond to this question in the chat. So if there are questions, please raise your hand. Okay.
There are a lot of questions in the chat.
Okay.
I can start from the last one.
I try to respond to some of them, but not especially to the. I mean, maybe Georgia, you can. So, okay. Sarah is asking: are there models that work at the urban or territorial scale that may be suitable for estimating local climate in urban areas derived by specific intervention?
Yes and no. I mean, urban area, then you're looking at really kilometer or even below kilometer. So they exist. It's difficult to run them for a long time because they need a lot of computation power. And there are other processes that might become very important, like turbulence, for example, that is parameterized again. And it's not the perfect parameterization. So until you're looking at maybe 2-3 kilometer resolution is not so important. When you go at 500 meters, then it becomes really important. So you need to test. And about climate change period from Giorgio Dalmasso, yes, you're right. Usually it's even 30 years, I would say, to consider climate change. But is the maximum that is achievable. So there is a new ensemble of convection permitting models, but it's only 10 years because the computational requirements are too high to run something more. So ideally, yes. Practically, no.
May I add something to this? Because this comes from the question by Saba. When does does weather become climate?
I know, that's another question, yeah.
I know, I think that Georgia was responding to this question.
No, I was responding to Georgia.
Yeah, who was responding to Saba, I think.
Sorry.
By the way, no, I want to just, concerning the weather and climate, I mean, I think that we can try to give like a statistical definition of climate, which is, if you think that climate has the probability of a weather event to occur, then you can define climate change. So basically, climate is the distribution of climate variables in general. It can be precipitation or temperature. If you, so climate change is basically a statistically significant change in this distribution. Of course, this distribution must be like defined in a proper time period, which is usually should be 30 years. 20 years is fine, 10 years also, depending on the context, of course, but I mean a time period long enough to define a PDF, so a distribution. So to detect climate change, you make a statistical analysis of your data. If you detect a statistically significant change in your distribution, then you have climate change, but you need to compare long enough periods. Okay, so maybe Lorenzo can ask his question.
Thank you. Actually, I have two questions, one for Professor Gaetani and one for Professor Fosser. And first one for Professor Gaetani is, when you spoke about the steady state of system Earth, I was wondering if it's correct to speak about like saving the Earth when using the communication for climate change and raising the problem to people, because as I know, system in steady states usually absorbs perturbations, and in this case, if the perturbation is mankind, what could be the consequence? And I don't know if I should let you answer and then make the second question?
Yeah, I can respond, answer quickly. I mean, steady states, it means that if you don't change the forcing, I mean, the system stay at equilibrium. If you change the forcing, like introducing more CO2, more greenhouse gas, CO2, we speak a lot about CO2, but there are many other greenhouse gases. You change the forcing, the external forcing to the system, and the system moves towards another equilibrium state, which is can be a warmer climate in general. This is what we are doing, basically. If you change the forcing like in a continuous way, you observe this continuous change. Concerning the expression of us having Earth, I think is not accurate because the planet is safe. I mean, is doing its life since like billions of years, and it will continue doing that. We have to save our environment, the environment we are living in. So, I mean, I think that maybe we can say, yeah, I would say the Earth environment or the human environment also. Human environment means that, you know, the general environment. Now it's like, I mean, I sometimes, yeah, you say Earth. I mean, the planet has been like evolving. The Earth system has been evolving through many complicated phases during its history. So we have to act now to save our environment and the climate. So basically keeping the forcing of the climate system like at, you know, please.
Thank you. And for Professor Fosser, when you showed a slide with the representative concentration pathways, and I see that in the worst case scenario, which is SSP 8.5, there is a point where it starts to decrease the carbon dioxide concentration, even in the worst case scenario. And I was wondering what could cause this plateau and then the decrease of CO2?
I think that, yes, I think that Roberto Bizzo can correct me, see if I'm wrong. I think that they assume that anyway technological changes would take over. It's just when these changes would happen. So it's like the world is changing that direction, trying to reduce CO2 and all the greenhouse gases. But the time that these will be required to do that is question mark.
Yeah, no, I agree. This is the main difference between these emissions, these concentration pathways, is when we invert the curve and we start decreasing. So the number reflects the radiative forcing in watt per meter squared that we will cause by 2100. So the smallest numbers means that we assume that we go down from emitting 50 gigatons of greenhouse gases today to zero by 2050, and then the others essentially shift this time closer to 2100. I don't think there is any point really in trying to do something even beyond that, because, well, let's see how we progress. And then this is why everyone stops in doing this projection up to 2100, no?
Thank you.
Okay, I don't know. Do you want to, Mario? Do you want we move to the next slot or?
Yes, we are perfectly on time, I think, so we can move to the next slot. I don't know if
because there are a couple of questions still in the chat, but maybe we can respond later.
Yeah, we are collecting all of them. Don't worry.
Thank you.
Good. So we can move on the last slot. I think the chair is Mauro Soldati, right?
Yes. Let's say that I will start.
Thank you.
And Marco Marani was the one who led the preparation of our abstract and coordinated our work. So if this is fine for you, I can share the screen. Can you see the presentation?
Yes, thank you. But not in full.
Yes, just a second.
Yeah, that's perfect.
Okay, great. So our presentation deals with the impact and adaptation, as you already know. And we have worked together to find a trade union between our expertise, which are quite different, but that have in actually impacts of climate related processes, mitigation and adaptation, common keywords and interests. So we, sorry, there is, okay. So we will deal with our presentation through a conceptual framework about natural risks with a special reference to some thoughts about changing hazards in a changing planet. We would like you to provide with some thoughts and issues that you may think of during your research, irrespective the main theme of your research. And then I will deal with that. After me, the probabilistic nature of natural hazards will be dealt with by Franco Flandoli and Augusto Neri, who will present a specific topic. And Alberto Godio will talk to you about glacial lake outburst floods, which are really an issue in high mountain areas nowadays, and extreme events in coastal areas and local effects will be dealt with by Marco Marani at the end of our presentation. So the conceptual framework and definitions of risk can be quite different according to different disciplines. Let's say that when we deal with natural hazards, geohazards, let's say the topic that are mainly dealt with in our CU, I think that we can agree on definitions, but this is anyhow a stimulus to collect perhaps different opinions on how we may define the component of risk. And maybe one day we may think about having a discussion involving all the CUs about definitions of risks. So here two events that occurred quite some time ago in Florence and last year in Germany, both very important floods that show how water created or regained its space in areas that were fluvial areas before, but after the city of Florence was built on the one hand, and after a meander was cut in Germany, that is of course just a specific, just a very punctual example, then we got into disastrous situations. So these are quite clear examples where hazards and vulnerability plus exposure interact, giving rise to a potential risk that in these cases became a disaster. So the risk components, on the one hand, hazards that we generally consider, and also at an international level, let's say, is considered as the probability that a certain phenomenon of a given intensity may occur in a certain area in a given period of time. So the questions that we have to try to answer when we have to define hazards are where, when, and how any potential damaging process occurs. Then vulnerability, the characteristics and circumstances of a community, system, or asset that make it susceptible to the damaging effects of a hazard. And we have to consider also exposure in terms of people, property, systems, or other elements present in hazard zones that are thereby subject to potential losses. So finally, in most cases, let's say in most research, we consider risk as the combination, the product, the integration of the hazard and the vulnerability plus exposure components. Very simple All formulas are reported in many scientific documents, and not only. And you can find sometimes the V and the E separate, and sometimes if you find just the V of vulnerability, this generally incorporates exposure, the concept of exposure as well. Sorry. Okay, so finally, we can consider hazard as, risk as the probability of occurrence of an event of a given magnitude, the cost of rebuilding the infrastructure, and the amount of infrastructural damage expected. Even if we try to have the best possible mitigation measures and adaptation measures, then there will always be, or in most cases, there will be a residual risk. So we have to be aware of that, that a risk may remain in an unmanaged form, even when effective disaster mitigation measures, adaptation measures are in place. So we have to be ready to emergency response also in those cases. Then there is another issue regarding acceptable risk. So as a scientific community, we may provide our statements, assessments, mapping of risks, but then who take the decision with our assistance and support, possibly, are politicians, are the decision makers. So then it is up to them to define which is the level of potential losses that a society or community considers acceptable, given a certain, given a series of conditions. We, of course, are experiencing this very well with reference to the pandemic, the COVID-19 pandemic. When we deal with mitigation, adaptation, residual risk, and acceptable risk, of course, we have to clearly consider the issue of return period, which is part of the definition of hazard, which is the estimate of the likelihood of an event, such as a flood, a landslide, or whatsoever, to occur during a certain amount of time. For example, if we say that a 100-year event is likely to occur, we indicate an event with a magnitude which is exceeded on average every 100 years. So in a changing planet like the one we are living on, managing the risk of extreme events to advance climate change adaptation shall consider very clearly and very thoroughly hazard. However, back in March 2012, there was a statement coming from a report of the IPCC where it was where we could read that disaster risk management and adaptation to climate change should more and more focus on reducing exposure and vulnerability and on increasing resilience and so on. From that time on, there was somehow at the European level, also with reference to funds available for projects, less attention to hazard. Because before there were many projects dealing with hazard assessment. And this led to a situation where hazard was somehow, the assessment of hazard was somehow neglected, which is quite problematic if we consider that a series of hazards, in particular hydromorphological hazard, are changing because of changing triggering causes, changing intensity, changing frequency. And so if we consider that the triggering causes, intensity, and frequency of these events are similar to those of the past, and we all know what happened in the past, and we therefore know what will happen in the future, we are finally wrong. We should not take this assumption and dedicate ourselves only to vulnerability and exposure assessment, which are anyway very, very important. So if we think about flooding, if we think about landslides, if we think about snow avalanches, if we think about coastal storms, gloves that will be dealt with later on by Alberto, we have really, it becomes really clear to us that their intensity and frequency have changed in the past decades. And therefore, a dynamic assessment of hazards should be envisaged to avoid, or let's say to get to a reliable and sound risk assessment. Of course, these hazard assessments should be based on continuous observation, monitoring of the relevant physical parameters, and considerations of the uncertainties involved. And this issue will be tackled later on. This implies the use of proper probabilistic tools to be coupled with ensemble models. And a central research need thus becomes the identification of proper time-dependent probabilistic models. I would like to recall the Sendai framework for disaster risk reduction that many of you certainly know. In these two slides, we have reported a series of links that you may look at when the presentation is made available. This is a framework that will be valid until 2030. So within your PhD program, your 3-year PhD program is certainly a document to be considered. It has 4 priorities for actions that are probably very close to many of the topics you are dealing with. So if you, when you have your presentation, when you have this presentation, you can click on the links here reported and find information at an international level, but also at the national level, because also ISPRA Ambiente is dealing with such issues nationally. So at this time, I would like to leave the floor to Franco for his presentation. I have indicated here my contacts in case any of you would like to contact me for any further information. I would like to specify, I didn't say this before, that I am a geologist specialized in geomorphology. Thanks for your attention.
Thank you, Mario. I'm Franco Flandoli. I work in probability, stochastic models. As I see also from the questions, the uncertainty is really something that puzzles everybody to understand it. Maybe another time we could decide to devote some time to some mathematics. This time to compactify a little bit the session, I just will pass the floor to Augusto, because essentially we work together to quantify the uncertainty of some geophysical problem that he will present. Anyway, all the session insists on a probabilistic assessment, fundamental. Also Roberto, all the talk was devoted to that. Some issues mentioned were the time dependence by Mauro just now, the time dependence of this probabilistic that should be updated during time because it changes. The fact that extreme events requires a probabilistic formulation, that maybe when the system becomes less stable, as it is perhaps our climate now, a little bit less stable than before, then the distributions spread and events which are extreme have more probability. All these issues are very important and are part of the message that we try to explain. So let me give the floor to Augusto and stop with our slides this short discussion. Please, Augusto.
Thank you, Franco, and good evening, everyone. I'm trying to share my screen. I hope I will be able to do it properly.
Yeah, good.
Can you see it, right?
Yeah.
Thank you very much. Okay, again, good evening, everyone. I'm Augusto Neri. I'm a researcher of Istituto Nazionale di Geofisica e Vulcanologia of Italy. And we are part of this PhD program since we funded one of the fellowship that will be carried out in this program. As Franco mentioned, we are working since many years in probability, specifically apply to the assessment of volcanic hazard and volcanic risk. And so today I will give you an idea of which is the type of problem we are facing in our field. Okay, first of all, I would like to say that volcanoes actually represent a serious, very serious geological risk, and they pose actually a major sustainability problem to the territories that are exposed to this phenomena. And this is true both nationally and internationally. In this map are reported the locations of the main volcanoes. As many of you already know, I'm sure, they are located, the volcanoes are mostly located along the boundaries of the tectonic plates. And we have about 1,500 active volcanoes, assuming the volcano that have erupted in the Holocene in the last 12,000 years. Of them, about 600 have been active historically. And this kind of problem, the hazard associated to volcanoes, to some extent is also similar, in addition to the fact that it is also affected to the climate change problem, since they are also characterized by quite long time scale as well as by extreme event. Here, I reported just 3 features of volcanic risk that make it particularly challenging. First of all, that about 10% of the total population worldwide live within 100 kilometers from a volcano, and so they are directly exposed to its hazard. Just a small fraction of the population experience actually personally volcanic eruption. So this means that there is a very low awareness of this kind of hazard. And finally, that they can have, in case of extreme event, really a potential global impact. Said this, I would like to remind you that Italy is actually one of the most exposed countries to volcanic risk. In fact, we have volcano, mostly the volcano in the Neapolitan area, in the Campania region, close to the city of Naples, that can actually have a major social and economic implication, not just for Italy, but also across the European Union. In this plot on the right, you can see we plotted the density of volcanoes in a given country versus the density of the population. And as you can see, Italy, together with Japan, Philippines, and the countries in the Central America are the most exposed countries in the world. And we have, to simplify the picture, six main volcanoes, one in the Neapolitan area and one in Sicily, in the Aeolian Island. These are the Vesuvian, Campi Flegrei, and Ischia in the first group, and Etna, Stromboli, and Volcano in the second group. Of these 6, 4 of them are presently in a yellow state in the alert level scales. That means that they are at the second level or 4 level. So they are quite in a quite active period. Just to give you an idea of the problem we are facing, I want to give you just a few more information about Vesuvian Campi Flegrei. The risk is actually associated mostly to the high density population living along their flanks or within the caldera of Campi Flegrei. And these are certainly 2 of the most risky volcanoes worldwide. Just think that about 3 million people are directly exposed to this kind of hazard, and part of them need also to be evacuated in case of an impending volcanic eruption. And as I mentioned before, Campi Flegrei since 2012 is in yellow alert level, and we are observing actually at this time a continuous inflating of the caldera floor. In the last 10 years, the floor has been rise up of about 80 centimeters, so it's quite a remarkable uplift. But these are not the only hazardous volcanoes we have. In the last few years, the other Sicilian volcanoes have been particularly active. They are associated to a lower level of risk, but they experience and they produce quite often eruption. In the summer of 2019, Stromboli had 2 major paroxysms, and just last year in 2021, Mount Etna experienced a series of several paroxysms that produce both lava flows and explosive column with dispersal of ash. Right now, we are facing a new volcanic crisis in the island of Volcano, where since the end of last summer, we are observing a significant arrest that pose significant risk to the local town of Vulcano Porto. So, but let's see briefly in what consists our work, in which way we quantify, we assess the volcanic hazard. First of all, we have to remind that volcanoes can produce a variety of phenomena. So per se, volcanoes are in fact multi-hazard systems. They can produce dispersal of ash, pyroclastic flows, lava flows, lard that are nothing else than debris flow composed by volcanic slurry of volcanic material and water, dispersal of gas, and so on. And the hazard has to be quantified in a strongly multidisciplinary way. So we need to integrate diverse methods in order to answer to different questions. Historically, they have been studied through the reconstruction of the eruptive record to answer questions like where and what could happen. Of course, we are monitoring them. We closely observe their status in order to answer when some event could occur. But personally, and in the ambience of this PhD program, we will mostly focus on the numerical modeling and numerical simulation of the volcanic processes in order to understand better how the processes develop and why they occur, which are the controlling processes governing them. And last but not least, a focus will be given to the quantification of the system uncertainties. Volcanoes are affected by different type of uncertainties and epistemic uncertainties due to the fact that we don't know exactly all the boundary conditions that govern their behavior, and also because they are stochastic processes, stochastic system, and governed mostly by the uncertainty associated to the dynamic of fluids. So in this way, by quantifying the uncertainty, we will be able to better answer questions like how much probable is a given event, how much accurate is our information. So just to give you an example of these two approaches that will be developed in the context of the PhD program, I want to show you the kind of modeling we typically do since we are dealing with the dynamic of fluid, a very complex fluid. These are not homogeneous fluid like water or air. They are usually multi-phase flow equation. So that means that we are solving, typically we are solving the compressible Navier-Stokes equation, not just for one single fluid, but for a number of fluids, each one representative of a specific component of our multi-phase mixture. For instance, we solve the conservation of mass, momentum, and energy for the continuous phase that typically is the gas phase, but also for the particles, the liquid or solid particle that compose the pyroclastic mixture. So I'm not going in detail. They have specific feature, this equation, like they're characterized by the introduction, for instance, of the volume fraction occupied by each part, by each phase, as well as by the interface terms that govern the momentum and energy equation. But just to give you an idea of the kind of modeling that we do, I would like to show you this picture and possibly a video that showed the evolution of the temperature of the ash erupted during a potential eruption of Mount Vesuvio, a subplinian eruption. This is the scale of the eruption that has been assumed by the National Emergency Plan in order to design the mitigation plan. And what is represented here are the two isosurfaces of the temperature. And I hope you can see this. This is the evolution in time of the eruption. We observe the collapse of the volcanic column. So this jet of gas and particle have been injected in the atmosphere, but since it is heavier than the air, than the atmospheric air, it collapsed to the ground and produced such very dangerous and devastating flow that are called pyroclastic flows. That, as you can see, just in few minutes, the video is about 15 times quicker than the real time, but just in few minutes, in about 10-15 minutes, this flow can affect.
Excuse me, Augusto.
Yes.
I don't see the movie. I don't know if I'm the only one.
Sorry. Do anyone see the video?
No.
No, we don't see the
sorry.
video.
No.
Oh, I'm sorry. I'm sorry about that.
So the video is appearing in another window, Augusto, or in the same presentation?
Yes. No, in another window. In another window.
That's why, because probably you shared just the screen with your presentation. You should. Should share the screen, the window with the video.
Okay. I'm not sure if I will be able to do that.
So you need to stop the sharing.
Yeah.
I can stop. Okay. And now you start the.
Sorry about that. So just the old desktop, you mean?
Yeah, that's easier. If you share the full desktop, probably try again. Yes, we see it now.
Okay. Sorry again. This is the evolution of two isosurfaces of temperature of the ash that has been erupted from the crater of Mount Vesuvio. And these two values are representative of temperature of 300 degrees Celsius and 50 degrees Celsius, the orange and the pink one. And as you see, we have a continuous feeding of the volcanic jet that produces a column that after a few minutes collapse to the ground and produce such dangerous, I was saying, and devastating flows that are called pyroclastic flows that can reach the coastline in about 10-15 minutes. And here are also reported the structures, the infrastructure, and the buildings of the town of Ercolano, and so this is just a way in which we can also represent the results of such complex numerical simulation in order to come up and communicate effectively scenarios to the population and to civil protection authorities. Moving on, I want to show you also that a way in which we use this simulation is also the production of hazard maps. In this case, in this paper we published a few years ago, together with Professor Franco Flandoli, we apply a simplified version of this model in a Monte Carlo procedure in order to simulate several thousand of simulation, changing different condition, changing the flow condition at the volcanic crater, and also taking into account every possible location of the volcanic crater in the way it will erupt in the next eruption. And we come up with maps of this type that report basically the probability of invasion of the caldera of Campi Flegrei in case of a next eruption for the next 50 years. And as you see, we have different maps. One is referring to the mean distribution of the invasion probability. The other refer to the 5th and 95th percentile of the distribution. So in other words, we try to come up with a reasonable value of the probability of occurrence, but we also provide uncertainties affecting such probabilities. And based on this analysis, based on this simulation, the civil protection authorities produce the map of the emergency plan of Campi Flegrei, designing an extension of the red area that should be evacuated in advance and of a yellow area that should be evacuated just in case the wind will blow in that direction. So this area will be affected by deposition of ash. My last slide is about another kind of problem, but to some extent similar. We are working right now on the production of another assessment at Stromboli volcano that, as I mentioned before, was quite active in 2019, produced again very dangerous pyroclastic flows. And we want to come up with a map of pyroclastic flow and LARS that, as I mentioned before, are nothing else than debris flow made of a slurry of pyroclastic material and water. And this is just an example of a volcanic process that can be affected also, can be influenced, but also by the climate change. So I hope I was able to give you just an idea of the kind of hazard assessment we plan to do and the kind of tools we are going to apply in this program. And of course, if there are any questions, I will be pleased to answer later on. I think I have to pass the floor to Professor Godio. Yes.
Thanks a lot, Augusto. I get okay.
Okay.
I'm sharing the video. And I start with my presentation. So, okay, is it clear now? Can you see?
Yes.
Yes, thank you.
Okay, thanks a lot. So for your attention, welcome to everyone. So I am Alberto Godio from Politecnico Torino. So I would like to introduce some basic concept of a peculiar phenomenon that occurring on the mountains. For sure is let me say, a phenomenon that is could impact also only some specific region. So I talking about Himalaya, I talk about the Andes, but also this kind of phenomenon could start to affect also Alpine region as well. So we are talking about glacial outburst flows. And please pay attention to this picture, which is a very relaxing picture showing a beautiful glacier reflecting on the water of a lake or just on the foot of the glacier itself. But potentially this lake could have a great impact, providing a terrific inundation on the village downstream. So we will discuss later about this example. So I would like to talk about this kind of events that the glacial lake outburst fluids, that are events that are also called GLOFs, that are events that could happen, let me say, suddenly, rapidly. They release a huge amount of water, and they, unfortunately, with no or little warning. So many cases, this kind of phenomena are unpredictable. So these phenomena could have a great impact on human communities living in the fluid path just downstream in the valley. And so we will try to focus on the description of the phenomena, how it's possible, if it's possible, try to predict this kind of phenomena, and which kind of action could be undertaken in order to mitigate that. So first of all, we have to define what is a GLOF, what is a glacial outburst fluid. So basically is generated because of a retreatment of, because of retreatment of a glacier provided for resulting in the formation of some lakes. These lakes are called proglacial lakes and are often bounded by sediments, boulders, and moraines. In some cases, we can also have a presence of existence of some lakes that are ponds distributed all over the glacier surface, and we call ice-dammed lakes. If a boundary of these lakes suddenly collapse, if it happens, could happen, so a flooding will occur downstream of the glacier lake, and we call this kind of phenomena glacial lake outburst flood. So 3 different characteristics distinguish these events. So they are a sudden release of water, sometimes cyclic, so could happen time after time. They are rapid events that could last some hours, and rarely they could exceed some days. And they involve a large downstream river discharge. Which is the impact? More than 1,300 glacier lake floods phenomena have been recorded in the past centuries with a great impact on the community, because more than 12,000 of deaths have been attributed to such floods. The most impacted region, if I mention it, are obviously Central Asia, Himalaya, South America as well, but also European Alps have been affected, impacted by this kind of phenomena. So this kind of hazard is related to intensity of the fluid, which could be released, could be caused by different trigger phenomena that we are going to discuss, and the probability of occurrence. I would like to focus on the intensity, because the probability of the occurrence of this kind of phenomena is a matter of debate because of a lack of a statistical information, of historical data, peculiarly in some remote regions. So we don't have enough data in order to build up a statistical distribution of this kind of phenomena. So far, we can distinguish the so-called moraine dam lakes. This is an example of moraine dam lakes in Himalaya. The lakes has been grown up rapidly since the beginning of the 6th of the past century, as the glacier started to retreating. So as you can see, it's completely bound by lateral moraine, by sediments that have been previously released by the dynamic evolution of the glacier itself, and is bounded by lateral moraine and a terminal moraine. So the amount of water which is nowadays stored on the lake is continuously growing because of the melting of the ice and the snow of the glacier itself. Other example of the lakes are the ice dammed lakes, which are formed when drainage of runoff snow and glacier and ice melting on the surface is trapped, is blocked by the glacier itself. This kind of phenomenon, this kind of lake, or better, the amount of water that is stored in this kind of pond is strictly related to the glacier mass balance, and could be strictly related to the climate condition as well, to the climate change as well. Which is the weakness of this kind of phenomena? The bound or the embankment, the dam of this kind of lakes are mainly compounded by ice that could collapse because of the action of the pressure of the water, and so a huge amount of water could be discharged downstream. So, but other kind of triggering could be analyzed. For instance, a very common triggering phenomena is the so-called displacement wave, or better, the calving of ice block at the glacier front that could fall down into the ice, could provide a sort of a tsunami, a water displacement that propagate all over the water, could reach the dam, and part of the water could overtop the moraine dams. And obviously, this is the reason of inundation on downstream. But other triggers could include, for instance, the rapid input of meltwater from the glacier upstream, rainfall. If the rainfall, snow melts, that could provide a rapidly increase of the water level of a lake. But other natural phenomena, could trigger the glove, could trigger the inundation. So for instance, earthquakes could provide mechanical weaknesses in the moraine dams and providing inundation. So other triggering phenomena of the glove, for instance, are due to the flowing of infiltration of water across the dam surface, which erode the channel into the moraine. This kind of process usually allows the moraine dam and lake to drain very rapidly. The terrific consequence of this kind of phenomena is consistent in the fact that the fluid water transport not only transport sediments, which might then develop and evolve into highly destructive, the so-called debris flow. Which kind of action? So this is just an example of, I call mitigation. Maybe it is, I exaggerate, but this is an action that we could perform and we could undertake in order to try to control and minimize the impact of this kind of phenomena. This is a typical glove which occurred some years ago in Italy, impacted with zero damages on the downstream filtering structure, on the valley. So this is the lake, the so-called Grand Clou Glacier Lake in Western Alps. And it originated again after 1 year. And after a couple of years, the stakeholder and the authority, the Civil Protection Authority, decided to undertake some different action. So for instance, they performed direct pumping of water volume using directly pumping into the lake to control and reduce the water level. And finally, a lateral chain was digged to slowly reduce the water volume of the lake. Actually, nowadays, so the lake is completely empty, and so the risk obviously is nowadays completely reduced. Other kind of action that could be undertaken are, for instance, try to predict possible scenario of fluid that are caused by the impact of avalanche and that could generate displacement wave. This is the example that we are mentioning before of the Palcochoca Lake in Peruvian Andes. And then when you can see that the triggering phenomena, the triggering cause could be due to the avalanche release from the mountain air that could impact on the lake and generate displacement wave. If we can assume different scenario. For instance, we can assume different volume of the material which could be released by the avalanche, such as we can just define large, medium, or small avalanche, and we can try to predict the impact on the downstream valley of a possible inundation or a possible flood. At the same time, we can try to predict what happens if the water level is maintained at the same level that is the standard level of a lake, zero lowering, or if we are able to, let me say, to undertake some action in order to reduce the water level, 50-meter lowering. Finally, obviously, the best scenario is we are able to reduce the level of the water inside the lake at, let me say, at least 30-meter lowering with the standard one. So in such a way, we can have a sort of metric of possible scenarios. Obviously, the worst scenarios is we consider no action in order to reduce the water level with the impact of a large avalanche. Okay, we can see in detail what's happened which could happen in the case of a worst scenario, where the 0-meter lake lowering is considering and the triggering because to a large avalanche is considered, is assumed as well. In such a case, we can see in this picture a detail of the intensity of the fluid intensity in blue, is here depicted, and how the floods could strongly impact with a community, with a village of Huaraz, which is located just on the foot of a valley. So the impact in this case should be really very relevant, and more than 50% of the village will be completely destroyed, which is the lack in this kind of simulation. So we are able only to simulate different scenarios of the intensity of a possible phenomena, but we are not able to say anything about the time of occurrence, the occurrence of this phenomenon, the return period of this, because of the lack of historical data about the previous phenomena. We only know in this case that terrific inundation happens for a similar phenomenon 17 years ago, but this is the only data that we have. So this was just a very short overview about, let me say, phenomenon, possible consequence of this kind of inundation. Just some final remarks on this presentation. So we can assess that glacial lake formation can be associated to climate change, okay, because the retreatment of glacier could provide for an increase of a number of lakes that are potential. It can cause potentially an inundation. We cannot say that the triggering phenomena that could provide disaster flooding, they are not often linked to the climatic factor. So it means that triggering phenomena could be, for instance, because of earthquakes that are a natural phenomenon, but it's not related to the climate change or climate effect, or some mechanical problem of a moraine dam could be are not strictly related to the climate change, and so. And also ice or rock avalanche that are common factor of triggering, they are not strictly related to the climate change. So even if the glacial lake fluids are not a novelty, because we have noticed about this kind of phenomena since many centuries ago, we are facing nowadays with an increase of this kind of hazard for sure, because in the last 50 years, we are facing a very fast retreatment of a glacier. How we can try to solve or to mitigate. So different mitigation action could be undertaken. They involve obviously monitoring with remote sensing, ground basing methods, sensor that could be located very close to the lake. Or better, we can try to model different scenarios in order to understand the possible impact of the flooding on the downstream valley. And obviously, when it's possible, we can try to undertake a direct action in order to reduce the hazard by drain the water in the lake itself. So thanks for your attention. Just some references in order to better understand the phenomena and the consequence of this kind of phenomena are given in this slide. And obviously, if there are any question, I am available for try to answer. Thanks a lot. I suppose that I have to give the floor to Marco.
Thank you. Yeah, thank you, Alberto. I will take it from here, share the screen. Here it is. You should now be able to see my presentation, hopefully.
Yes, thank you, Marco.
Okay. So my task is to keep you focused for these last few minutes of a long day, an interesting day. I'm Marco Marani, and I'm from the University of Padova. I'm a hydrologist as a training. My research focuses on water cycle and in general, and on the evolution of coastal areas, in particular, lagoons and estuaries, also as a result of climate change. Today, I will focus on extremes, on some definitions, and I will try to touch upon some points that I think are methodologically important to clarify often some misunderstandings. If we look at projections, and we've heard quite a bit about models and our improved understanding of the climate system, we know, although with uncertainty, we know, and this is the upper panel in here, that there would be changes in the water cycle, and some of these changes are related to changes in the annual mean precipitation that you see here, and that's not going to be uniform over the globe. You're going to have areas in bluish colors where you will have an increase or increase is expected in mean annual precipitation, whereas other areas in the say brownish colors where a decrease in precipitation, in annual mean precipitation is expected. But if you look at the panel below, where we're looking at changes in the wettest day of the year, meaning the highest intensity, highest yearly intensity in rainfall at a given place, you will see that the color bar here indicates that we expect increases in rainfall intensity, extreme rainfall intensity. That's going to be it's going to be heterogeneous globally. So we'll have hotspots of increase in rainfall intensity. We'll have areas where this increase is less, but clearly we have to be prepared for changing hydrologic cycle, and in particular, rainfall in this case. So one of the tools, and Mauro talked about this concept, I would like to elaborate a little bit on it, the return time concept, because it's crucial and it leads to many misunderstandings in my view. We need an index that's telling you how extreme is an extreme. And commonly we use the return time, which is the average time to the next exceedance of a value. So if I have a certain value X, and in this case, this is the water level in the River Nile. So if I'm looking at a certain value X, and I'm looking at the record, I can find when I have exceedancies, and you see these red dots of this fixed value X. And I will then be able to identify times between exceedancies, T1, T2, T3, and so forth. And return time is the average of these values. So the return time is an average. That's very important to keep in mind. And it helps us characterize how the degree of extraordinariness, if you want, of an extreme. If I take a different threshold, a lower threshold in particular, you see that the inter-arrival times of these exceedancies will be shorter because I will have many more of them. And so the return time, which is the average of all these inter-arrival times, will be lower. So the return time is useful in characterizing how extreme is an extreme. But it might be very deceptive as well. When we talk about the 100-year event, as was mentioned before, that's the event that will be exceeded on average. And on average is key here. It's exceeded on average every 100 years. And that means that doesn't mean it will not happen next year, of course. And we have to bear in mind that even though the return time looks very long, so a very unlikely event, the 100-year event has really a 68% probability of occurring in your lifetime. So if I were you, I wouldn't bet my money on it. And actually, we must be very careful when considering this type of characterization of the degree of extraordinariness. We use this concept all the time to design adaptation measures. The topic here, the theme here is impacts and adaptation. So how do we design adaptations? They can be very varied. It can be simply planning of different types, decisions that are made of building infrastructure in a place rather than another. But oftentimes you have infrastructure that's been evolving over time, and you want to decrease the potential risk, or you want to decrease the risk that is affecting the existing infrastructure. So you have to build these types of works. For example, a reservoir to mitigate floods. What's the return time we typically focus on? These are return times of the order of hundreds of years. These are the type of events we want to be able to control to avert damage and loss of human life. Same goes for when I build such a reservoir. An important element is the spillway, is what allows water to go through without destroying the dam, which would be catastrophic. So we need to design the spillway in such a way that a large discharge will flow through it. So, and in this case, because the outcome will be catastrophic, the return time that we choose is very high. It's of the order of 10,000 years or more. For bridges, which are very common everywhere, the return time we use is 200, 300 years, depending on the size of the bridge and the importance of the bridge. But how do we determine the event that corresponds to these return times? These return times are fixed. So we want to design our infrastructure and our mitigation measures based on these return times. We have to find the corresponding event, size of the event. So let's focus on rainfall. This is an analysis that is taken from a very long time series that is a series of daily rainfall observations in Padova that has been started in 1725. So it allows us to look at, it provides a window, a particularly long window over our past. And what's been done here, I will not deal with how it is done, but we can infer the 100-year rainfall, daily rainfall in this case, using sliding windows over time. So for sliding windows of 30 years in length, we can determine the 100-year event over time. And you see that there is a large variability in these extremes. And the variability is very problematic. We don't know how to deal with it. And think about a bridge that would be built, say, in 1919 at this point in time. And I have, this is what happens typically. I have 30 years of observation. We don't have, very often that's all we have. And based on these 30 years of observation, we were able to say that the 100-year event is, say, about 125 millimeters per day. And so we design our bridge based on that number. But then the bridge has to last for 100 years. And really, the extremes that actually invest that bridge are much higher than previously designed. So there is a lack of ability on our part to incorporate this type of variability in our design practice. We really don't know how to do that. We know change is coming, but we don't know how to deal with it. We know, as Yogi Berra, this baseball player, nicely put, we know that the future is not what it used to be, but we don't know how to behave, how to better design our infrastructure, because we don't know how to predict this in simple ways, these varying probability of occurrence. Now let me take you for a short ride on problems that have to do with the coast and Venice in particular, which is arguably an example, an important one, a paradigmatic example of a vulnerable site where both with importance that is both cultural, and economic. And Venice is really an example, but many cities are actually exposed to similar risk. And we know that London and St. Petersburg already have built protection measures. Also, that happened also in the Eastern Scheldt and in Rotterdam. And protection measures are being planned in Houston, Boston, New York City, and in many other major cities around the world. As you may know, recently, the MOSE system to protect the city of Venice has become operational in order to protect the city from this phenomenon that you see here. This is the change in mean sea level that is projected over the near future in Venice based on IPCC RCP 8.5 scenario. So what will happen in the future due to, associated with these changes? Well, there has been one event that has been very important, 1966, the big flood, in the great storm surge in Venice. And let's take this Canaletto painting to try and visualize what happened in Venice. This is St. Mark's Square in Venice, and we'll take these two characters in the painting to show you what happened in 1966. This is the amount of water that was in Venice in the St. Mark's Square on 4 November 1966. The same storm in 1750, at the time of when the painting was painted, this would have been the level. So fairly high, but not catastrophic. Looking at projections, this is what we expect to see in Venice for a similar storm surge occurring. So this is basically the reason why this system has been built, is now operational. It has avoided flooding of the city many times already. And we might want to, with the tools that we discussed today, understand how safe it is. So the design event of the MOSE system is a very high one. It's 300 centimeters above datum. And this currently has a return time of almost 20,000 years. So very, very small probability of occurring, very, very small probability that the MOSE system will be not sufficient to protect the city. But we see here on the left that if we account for sea level rise here, this difference, 48 centimeters to the end of the century, then the design event becomes much more frequent, still fairly infrequent, 3,000 years return time. So we can conclude that we should not be worrying about the MOSE system failing. But here, the problem is that because we'll be closing so many times, and this is the number of days that the system will be closed during 1 year on average, we can see that we start out with basically about 7 days per year of closure, but at the end of the century, we project 260 days per year of closure. So that's clearly unsustainable. Clearly, the city and its lagoon will be very different from what they are now because of so many closures. So even though we might be able to protect the city, the environment around it and the life around it will be highly impacted. And I won't go into the details because time is short. We showed recently that because of MOSE closing so often, this environment, these salt marshes and tidal flats and so forth, are becoming more and more fragile with respect to sea level rise. So they have, by closing the MOSE, we're actually endangering them even more than they are already because of sea level rise. So just a couple of take-home messages. Remember, we use a lot this return period concept. It's an average. Beware, it's falsely reassuring. A 100-year event is actually fairly frequent. We know extremes are increasing, and we need better ways. That's an urgent need. We need better ways to design infrastructure to account for climate change. We talk about climate change, we understand it better. We don't know exactly how to act, and that's an urgent priority. And then I would like to point out to what I call the short blanket syndrome, meaning, of course, you can put in place many measures like MOSE, but it's a short blanket. I mean, you mitigate one impact, but you create another one. You have to expect collateral damage when you put in place mitigation and adaptation measures. And with that, I thank you. And I think this will probably conclude our session. I don't know if Claudia wants to take over, if there are any questions or any discussion.
Thank you, Marco. Thank you to everybody. It was very interesting, I think. I reached in suggestions for today. We are a little bit tired, I think, but if there are some questions for Marco, we can answer to someone. For example, Federica, do you want to ask something?
Yes, I have a question for Mauro Soldati, Professor Mauro Soldati. Yeah, you talk about the risk, and I think that you are a coastal geomorphologist. It's correct, no?
Coastal and mountain, both.
Okay.
Depending,
so,
yeah.
Okay, yeah. I'd like to know if you did study about the shoreline evolution in a short time interval or not, because you talk about the coastal risk, and when I think about it, I think coastal erosion phenomena.
Yeah, when I've dealt with coastal risks, I have been dealing especially with landslides, a coastal landslide in high coasts, and this was made essentially in the Maltese Islands. More recently, we have started dealing with sea level rise and the impact of sea level rise. So this is a long-term process, but there is among you as PhD students, someone, and I'm referring to Nabanita, who will take care of the interaction between this long-term process, which is sea level rise, and shorter term processes like marine storms and other potential hazardous processes that may occur due to climate change. I'm referring to extreme events that are adding to the effects of sea level rise. So it is one of the aims of the thesis, of the research, to deal with both long-term and short-term processes. But so far, personally, I have not dealt with the processes you were mentioning before.
Okay, because I request you, because as you know, during the events of last week of Curriculum 1, during my PhD project, I will analyze the sea level rise. But as I told last week, I won the national competition of this edition of GNRAC, Gruppo Nazionale di Ricerca sull'Ambiente Costiero, and we are working about the evolution of the shoreline using numerical modeling. So for this is a curiosity and extended also with other professors, I don't know.
Yes, I think we can stay in touch, and you also can stay in touch with Nabanita and discuss about your ongoing research. I think it will be beneficial for both of you and of us also as tutors of your thesis.
Okay, thank you.
You're welcome.
Thank you so much. There are other questions or comments about that? Roberto Guizza. Please.
Yeah, I just want to try to summarize a couple of messages that I would like you to take from today. First one is that today, thanks to advances in theory and to the availability of faster computers and free availability of more and more observations, we know more than ever about the Earth system. And we have been developing tools and methodologies to try to understand what's happening and to predict what will happen in the future. Clearly, the models that we built are not perfect. They will never be perfect. So there is an issue of the uncertainty in the observations, uncertainty in the models. But what we are doing today compared to 20, 30 years ago is that we are trying to use theory and numerical method to estimate the uncertainty around our estimations of a current state and of a future state. So this is the basis this is how we scientists work. And when you read, for example, IPCC summary for policymakers, or when you read reports that try to estimate the economic impact of decarbonization or of a carbon tax or whatever, you have to imagine that behind this type of reports, there is all what you heard today. So there are models built on knowledge, and clearly they're not perfect, but this is what we have. And I would say that decisions based on this type of studies are much better than decisions based on either single forecast or no forecast at all. It's also, as you have probably understood, especially from the last talk, it's clearly necessary that we try to build dynamical models of a system we are dealing with, because the past statistics, what happened in the past, might not be a good predictor for the future. In a changing climate, the frequency of extremes are changing. Events that in the last 50 years, as you heard, where maybe had a return period of hundreds or thousands of years, with a changing climate are becoming much more frequent. So this is why we need research in these fields, and we need that people working in other areas, economists, engineers, expert in agriculture, or legal expert who wants to estimate the risk of potential damages to society, take this into account and use the most updated results. I hope that today we've given you a feeling of what's behind the reports that I mentioned and that you read on sustainability and climate change. I don't know whether some other colleagues want to add something, but really what you heard today is something, it's the state of the art, it's where we are. And it was great to hear so many experts coming from different fields talking about uncertainty, models, predictions, as we did today. So I give the floor back to Claudia. I don't know whether you want to add something, or other colleagues, or Mario.
Yeah, maybe let me just say thank to all the speakers, and especially thank to all the PhD candidates here, that they have survived to such a long day. And also just after the end of the session, I'll send to all of you the link for the learning test. I repeat, this learning test is especially important for us to understand how much of what we wanted to deliver has been actually received from you. So please feel very relaxed and just do your test without sharing the information with your colleagues. For those who are not able now, they can complete the test later on, but probably it's better to complete the test now. And also your colleagues that were not able to attend the online seminar, they will, attend them thanks to the recordings, and they will do the test later on. Okay, that's all for today, I think. I don't know if there are other comments or messages. I think we'll meet again tomorrow at 11 a.m. So please take a rest this evening and be prepared for another long day tomorrow with an interesting webinar. The program that I sent to you today, it's a light document because there could be some variation or modification. So the link will stay the same. Please check every day that link in order to read the program and the biographies of the speakers. And there are also a list of references there. Marco and Georgia, I think, will help me to elaborate all the questions that you wrote in the chat box. And we'll try to send to you as soon as possible the answers provided by the speakers today. Thank to all of you.
Mario,
yes, Roberto.
Mario, say something about where they will find the PDF of all the presentations.
Yes, sorry. Yes, thank you, Roberto. Very important. We are also uploading all the presentations in a PDF format in a shared folder. I'll send you the link today. Probably they will be available at the end of the day, so be patient if you don't find them. You do not need the presentation now to do the test, but just do the test with what you actually have in your mind at the end of this long day, because it's really important for us to understand if this format of the webinar was actually good for all of you. So feel really relaxed to do the test. Any other message, any other information from the audience? Yes, Marco.
Just one last comment. I see that in the chat there has been a discussion about, to go more in detail about, some issues related to social impact and social risk, and also treating uncertainty. We will keep track of all your comments, and I think that in the panel we will discuss how to maybe organize more discussion about that. So thank you. I mean, I think this is a very, maybe the most important result of this day. This first day that there has been a discussion in the chat among the students concerning, more inputs. And so thank you. Very well. Well done.
Yeah. As we were discussing yesterday during the meeting, these are webinars where actually we give a presentation and you can make questions. There will be a workshop or something similar to a workshop where we will give to you the floor, okay, to present and also to propose, and we have some ideas on how to work in teams and so on. So we probably in the next webinars you probably have also more space for discussion depending on how the day has been organized. Today was really useful, the questions and the suggestions in the chat. Thank you very much. We'll meet you tomorrow, the same link, same organization. So have a nice evening. Bye. Bye-bye.
Bye-bye. Thank you.
Bye. Thank you.
Bye.
Bye.
Thank you so much. Bye-bye.
Bye.
Thank you very much.
Bye.